Is there a trade-off between the benefits of machine learning and privacy, in particular when it comes to sensitive data? Today, we will explore these questions, first with some theoretical perspectives on AI and sensitive data, and then we'll have 4 more specific examples or domains: medicine, finance, the military, and research. So looking forward to this. My name is Dag Stenvoll. I'm the coordinator of UiB AI, which is an administrative function at the University of Bergen to promote and visualize and try to strengthen the interdisciplinarity of AI research. So we have a steering group with representatives from all the faculties. So the idea is to put people from different disciplines in the same room and see what happens. And this seminar in particular is in cooperation with NORA, the Norwegian AI Research Consortium. We do this maybe once a year, and we're happy to have NORA here to cooperate with them. They also represent the UiB and 16 other Norwegian universities and research organizations. They also have a lot of interesting seminars, and they stream all their seminars like this one, so you can check their website for seminars in NORA and also UiB AI. We have about 100 people signed up physically here in the university aula, but we also have about the same amount who signed up on the streaming. So welcome to you also who are following this on stream. And it's also possible to see the recording of this seminar after, if you want, on the UiB YouTube channel. So without further ado, I'll give the word to Inge Jonassen, who is a professor and the head of department here at the Department of Informatics at UiB. And he's also the leader of the steering group of UiB AI. So please, Inge, come to the floor.
Thank you very much, Dag. So I have a clicker somewhere. Yes. So I'm just going to give kind of an overview presentation with some of the aspects on the potential of using sensitive data in AI, what is actually considered sensitive AI, and some thoughts or perspectives on regulations and practical ways to actually do research on sensitive data. So maybe the most popular use of AI is to things like ChatGPT and so on, that people use also for leisure activities. And the top leisure activities includes things like company and therapy and purpose finding. So this is you can consider sensitive uses. But this is not the focus of my presentation, not the focus of today's seminar, but it's still kind of a perspective on AI and sensitive data as well. But in this case, it's very much up to the user. This is a guy using the ChatGPT as a companion or a romantic affair, and a woman using ChatGPT to organize her life, both generated by AI, of course. In industry, which is more interesting, some of the top applications, I don't know if this is really the top 10 applications, but it's a nice illustration anyway. There are applications towards healthcare, finance and banking, retail, e-commerce, and some of these domains, in particular healthcare, is of course involving what we call sensitive data. Data about your health, about your genetics, and so on. So this is more in context of what we're going to talk about today. So what data is really considered sensitive? When it comes to personal data, according to the GDPR, the General Data Protection Regulations, it's data, for example, about racial or ethnic origin, political opinions, religious or philosophical beliefs. And so you can read the list here. I'm not going to go through it. But these are things that we do not necessarily want to share about ourselves when we are dealing with a company. So this has a consequence if this is shared freely or used for a purpose that you would not agree to at the outset, this has the consequence for you as an individual. So that is sensitive because it has a consequence, potential consequence for yourself. So the use of this kind of data is regulated, and of course that's the kind of trade-off that we are discussing today. The protection of your own interest as a person and the potential that lies in this data, for example, to provide better healthcare and so on. So it matters what kind of purpose you will use the data for. If you're going to use the data to grant a loan or to grant social benefits, for example, this is a decision that has a consequence for an individual or, in other cases, for a society. And then the data becomes sensitive and needs some protection. Also, business data can be sensitive. You don't want your competitor to know everything about your sales and your strategies. Data about critical infrastructure, the electrical system in a country, the water system, and so on. Cybersecurity information is sensitive and needs protection. And of course, defense data about how the military operations, the setup, is sensitive because it has consequences if this falls into other countries' hands, for example. When it comes to regulations in the European Union has one of the first general regulations of AI, and it divides the different uses of AI. So there are uses that have an unacceptable risk. So this is data, for example, if you use AI to recognize the faces of everybody passing through the city center or wherever, tracing people and tracing their behavior, this is unacceptable in EU. This is something you cannot do. Then you have the so-called high risk, where the AI is helping or making decisions that affects individuals or affects companies and so on. So this has an impact on health, safety, or fundamental rights. And in these cases, the regulations are quite strong. And this is about the applications of AI, but it also has a consequence on the data that is used in this. So these are two sides of the same coin in my thinking. And then you have a lower risk, where you have a risk of impersonation, so videos of Trump making strange statements. That doesn't have to be AI, but things like that, where you want it to be labeled as AI. So and you want transparency in the use of AI in a context like this. And then, of course, you have minimal risk applications. So, this AI Act comes on top of the General Data Protection Regulations, which has a protection or phrasing about the sensitive personal data, that this cannot be used. But there are exceptions. So processing of personal sensitive data can be allowable if it is necessary for reasons of substantial public interest. So in context of AI, this can, for example, be if you use AI to decide whether a person should get social benefit allowance. There might be a fear that you discriminate against people of a certain ethnic origin or a certain political belief. And in order to protect against that, you may need to know something about these groups. And in some cases, it's then allowable, according to the new AI regulations, the way I understand it, to actually use sensitive data in the training of the AI system in order to ensure or try to counter against such discriminatory behavior of the trained AI. So it's not straightforward in all manners, either the regulations of AI. We're not going to talk only about industrial applications of AI. My perspective is more on the research, but of course, and the AI Act has an exception for research, so we can do research on systems for providing diagnosis, for choosing treatment of patients, as long as we do it in a research setting. And there are specific regulations for what we need to think about that I come to next. But of course, when we do this sort of research, we would also like to have in the back of our mind, and maybe not so far back, if this can really be applied in society as well. And then we need to know about the regulations that apply to non-research applications, so real applications of the systems that we work on. When it comes to research, EU is trying to strengthen the research on AI in Europe, and it launched the Apply AI strategy in October last year at a summit in Copenhagen. And some of the main focuses there are in healthcare and pharma, and mobility, transport, and automotive, and so on. You can read the list here. But healthcare is among the top application areas, and that really relates to and uses sensitive data, as we will hear more about. When we are doing research at the university, we need to adhere to the regulations also at the university. And if we will hear more about this from Christine Stansberg later today. But we have different color codes of the data that we can use as university employees. And if the data that you're dealing with confers a risk towards a harm for the university or for individuals, it is considered strictly confidential. And then should be treated only in the safe system that is made for this kind of data, or in eForte or a WebSock that is a more administrative system. But for research context, it's the safe system. So and other universities in Norway and elsewhere have similar regulations that we as researchers need to adhere to. So we will hear more about safe later on. So when we do research on sensitive data, we need to store the data in these secure places. That is at least the default way to do this kind of research. And in typical medical applications, the project owner needs to have an ethical approval to collect this data. So it could be data on genetic variants or on other health variables of a set of individuals. So he will have a REC or ethical approval for the project. And the owner of this needs to decide who gets access and what can be done on the data. A point I want to make is this still gives a chance for open science, but when you share the data from a study with others, you need to make sure that the new use of the data by the secondary use should be in adherence with the consent and the regulations in the country where this was given. The data should still be stored in a fair fashion, so to be findable, accessible, interoperable, and reusable, so that people can control what you did and check that your findings are really valid, but also reuse the data in other settings. So when it comes to genetic data, you would, for example, have the genome sequences or parts of that for a set of patients. And in order to collect that and use it in your project, you need a consent and an ethical approval, as we said. Often this kind of data is, by legislation, not permitted to leave a country. So that's the one aspect as well. But when you think about reuse of genetic data by others, you may want to find the data in two different ways. You may want to look for other studies in diabetes patients, for example, or leukemia or whatever, So it would be nice to have a way to find other studies that have been done on a particular disease. Or you may want to find studies where there has been a particular variant discovered. And these are two ways to query genetic data sets. When you found a data set, you may want to get access to that data set, to get the diabetes patient data to help your own study. And then you want to download this data and use it again. And there are research infrastructures, such as Elixir, which is a European research infrastructure for biological data, that has services that does exactly this. So we have something called European Genome-Phenome Archive, EGA, that was set up in 2008. So this has been going for almost 20 years. That does exactly this. But since the last years, since 2022, there's also a federated version of this, where we have data, for example, in Norway, from Norwegian patients that you need to access or contact Fegar Norway to get access to those data. But in order to find that there is interesting data in Norway, you can go through the central EGA and find the diabetes data sets, for example. There might be some in Norway, some in Spain, some in Germany, and so on, and then you get access to those. So this is, then you get access to the data, and it's accessible in a standardized manner. And for this, we use global standards, not European standards. So there is a global alliance for genomics and health that works on a global level to make sure that the data can be processed in the same way, both for AI and for machine learning or other data analysis approaches. So this is an example, and this is quite a big field of sensitive data worldwide. But of course you can do this kind of things with the other types of data as well, to set up systems where you have access to metadata and then controlled access to the real data, and making sure that data is fair and that it's represented in a way that is standardized, so that you can use data from Norway, Spain, and Brazil, for example, without too much problems. And then lifting the insight into diabetes, for example, by being able to use the data from across. So a bit of something about machine learning and applications as well. Of course, artificial intelligence contains different elements. I'm going to focus on machine learning and say a few words about what really needs to be protected in a machine learning setting. If we think about the classical machine learning process where we want to learn a classifier, we are having training data, we have a learning algorithm, we derive a model that we can use on some input data to get the class for a new example. So for example, learning different subtypes of diabetes or cancer, or who should get a loan, who should not get a loan. So of course, in this context, the training data and input data probably contain sensitive data. So this could be genetic data, for example. And then it's a question whether the model as well is sensitive. And this depends. If you have a really large neural network trained on a relatively small data set, you may be able to reconstruct the individual training data from the model. While if you have a really large data set and a more simple model, it will be impossible. So there are, of course, many studies into when it might be possible to reconstruct individual data from the model. And this is relevant, for example, for federated learning, where you may have different data sets, for example, residing in Oslo, in Madrid, and in Rio, in this diabetes example. You may want to learn a model from the data in Oslo, from the data in Madrid, and the data in Brazil, and then share these models and make a supermodel that summarizes all of this. In a simple manner, this is what is happening in federated learning. So then, do you also need to protect the model, or do you need ways to protect the model as well? And that depends on what kind of data, model that you are using. Of course, you can also do other things than just putting data inside these protected environments. You can do encryption, that we will hear Håvard talking about later, and do the learning maybe on the encrypted data. Then you will never release the data in itself, and if the encryption is good, the data is safe. There are also differential privacy approaches, and there are synthetic data approaches that allows you to do useful analysis of the data or of a variant of the data without revealing or risking the original data. And there's a balance between the privacy, if you make synthetic data that is very different from the original data, and the utility. So in that case, it may not be so useful anymore if the synthetic data is very different from the original data. And this is a whole field, and I'm not going into details, but we get some glimpses of other approaches in the seminar today. So, AI on sensitive data, this includes many important application areas, of course. This both in research and in industrial and government applications of AI. With us, it's regulated. We are not part of EU, but of course we are there, and we implement the AI Act. And this regulation is currently being adjusted to make it less strict, so it's important to follow that. An important point I want to make is that sensitive data can still be shared. So it can be shared as open as possible, but as closed as necessary. So through these controlled access mechanisms where you share metadata. And we can do research within these approved safe environments, or trusted research environments, as they are also called. And there are other ways that we can do processing, safe processing of sensitive data. So we'll hear more about that today and the trade-offs in different applications of AI. That's what I wanted to share.
Thank you, Inge. And since you finished before time, I think
Yes.
we can take a few questions and comments.
Very good.
I was thinking that at least one key takeaway for me is that we should protect ourselves when we engage with AI, especially as partners, sentimental partners. Anyone? Questions or comments to Inge's talk? Everything's super clear. Anyone? Yes? Just a way to have the microphone. Can you say your name also, please?
Hi, Camila. I have a question, but it's not really connected to the sensitive data. For example, yesterday I have make a question to ChatGPT, and the answer was wrong. And it was a really popular answer that I was looking for. So who is the responsible for that mistake? I wonder if there is any answers to that right now, and it will be in the future. For example, if I have to give that answer to a user, to a client, is my fault, is his fault, is the developer mistake, ChatGPT, who's gonna blame for that?
So you're thinking, for example, if a student with us uses ChatGPT on an exam and only gets a C, he may want to sue OpenAI to get a B. So no, I'm not aware of the legal status of these things, but when you use ChatGPT and these other large language models, you are made aware that this is an artificial intelligence agent, and that that they are not responsible for the accuracy of the results. They cannot guarantee the accuracy of the results. So I think that's a standard thing that comes up every time you open one of these services. So it's on you to check, and that would be my advice. When I use this quite a lot myself, and then I always I appreciate when Copilot, for example, that we have now through the university, also gives references. So I can go in and check whether it got the data correctly and it looked at the right things. So that's my advice. And I think in practice, the responsibility is on the user at this point. I know there's a lot of work that is being done to patch, to help the large language models to quality control the results so that you can, to a larger extent, believe the results. But so far, the responsibility is on you.
My name is Helen. Would you please go back to the last slide you used? Because my question is directly associated with that. The very last slide.
This one? Oh.
No, the last slide when you have a conclusion.
Ah.
Yes, and the very last sentence.
Yes.
Yes. I am struck not only by the content of your talk, but also the spirit. And I love the positive thinking and forward-thinking spirit. And I think this is crystallized in the verb choice you made in the very last statement, multiple ways to enable AI on sensitive data. I think that kind of immediately corrected my bias. Normally, we think of AI almost automatically equals exposure and then danger. But you are saying that, well, let's think about from the opposite side. So it's not that multiple ways to control AI and then prevent them from exposing or misusing sensitive data, but rather to enable AI on sensitive data. I found that to be very, very inspiring. So my questions are twofold. First, what is your mindset and attitude and rationale behind this kind of very, very positive, verb choice, which really create a kind of spirit among these not only is AI already friendly community, but also help us gain more AI, not AI focused, but rather really concentrate on the synergy, the optimal synergy between AI and human. And then the second question, if you have time, but only if you have time, can you give us an example how concretely and exactly to enable AI on sensitive data? Thank you.
Okay, I'm not sure I got all aspects, but my thinking is that the regulations and also my own ethical concerns about use of sensitive data makes it at the outset challenging, difficult to do AI in a meaningful way on this data. But there are ways, so that's my message. Also, both in the research era, where we have these safe systems, we have the ways to have controlled sharing of research data, even though it's sensitive. So there are multiple ways, and we'll hear about ways to have this privacy-enhancing technologies, including encryption, as an alternative way. So that's maybe the positive. I try to be solution-oriented, look for the possibilities. About the other thing, so for example, use of sensitive data that has been successful, was that the question? So there are examples, of course, of using genetic data from studies, reusing them to strengthen findings, associations between certain genetic variants and disease types that will help choose the right medication. There are another example that comes to mind is use of prescription registry data, where people have found that use of a certain drug comes together with lower incidence of a particular disease later in life. So if you can use prescription data together with, prescription data together with cancer registry data and other disease registry data, you can view the medication of a population as an experiment, where you have done given people drugs, and then you see later which other diseases they get. So certain medication was found to be protective or give a lower incidence of Parkinson, if I remember correctly, for example. And that can also give clues to mechanical insights into the mechanisms underlying the development of these diseases, and you may even be able to make better drugs. But already you have repurposing of a drug. And of course, there are many examples where you have, in rare diseases, you probably have, well, I've been doing research on leukemia, particular types of leukemia, where we have, luckily, very few patients in Norway. But if we can also include patients from Canada, from US, from other places, we get enough examples to find the clues of how to better treat these patients, using both AI and systems biology modeling approaches, for example. So there are many potential applications, but so it's dangerous to shy away from all use of sensitive data, because then you lose all these opportunities. So I'm thinking that the regulations that we have and the mechanisms that we have around enabling use of registry data in Norway are too strict. We are losing out on our opportunities, and that's probably, well, in my mind, ethically challenging as well. Of course, we need to protect the privacy of people, but we also have obligations to use the data for the best.
Thank you. We have time for one final question.
Yes.
Thank you. Thanks, Inge, for a very, very nice introduction to the whole day and a really nice overview of the field. I've enjoyed this. My name is Sushma Kralscheid. I head Elixir Norway, and therefore have a lot of interest in these kind of topics and questions. So what I was thinking is, with increased uptake of AI across the board, and an increase in trust towards AI, even though it has its defects, we are starting to learn how to use this tool in a sensible way. And what I worry about is, A, are we sufficiently educated in how to correctly use it? This is a learnable skill. And two, I wonder whether we are sufficiently resourced in terms of infrastructure for compute power and for existing infrastructures to enable these kind of approaches. And I just wondered if you would reflect on that.
So I think the expertise into AI methods on the methodology level, based on mathematical and computer science, physics, whatever research, needs to be strengthened. It's quite good, but it needs to be strengthened, and we are having the AI centers in Norway to help do this. But I think what is more lacking is also the insight from the application field, from the medical researchers, from the biological researchers, and this interdisciplinary expertise where you need the domain insight coupled with methodology expertise. So some of the AI centers are also linked to application areas and will be able to lift that. But it's not really a big investment from on the Norwegian side. So and the EU is also seeing this. The EU is putting a lot of money through the RAISE program and through other programs to help increase the capacity and the competitiveness and the sovereignty of European research on this, but of course also industry. On the infrastructure side, we are also lagging behind. So we need more investments into machines able to do the large analysis, train the models and so on. And they need to be set up in a way to use on sensitive data as well. And we have the know-how how to do that, but we need more investments to scale this up.
Thank you, Inge.
Okay, yeah, very good.
So, yeah. Our next speaker is Håvard Raddum. He's Chief Research Scientist at Simula UiB. And when I Googled Håvard, the first thing that came up was a seminar from 2009 called Cryptography and Murder. So today it's going to talk about how to do machine learning on encrypted data. Less juicy, but nevertheless interesting.
So, yes, I have my slides as well. Okay, so I'm a cryptographer doing cryptography research. So now I'm going to teach you a little bit about how we can use cryptography as an enabling technology to actually solve some of the problems that were asked about and that Inge talked about in the end here. So, because I'm a cryptographer, it's going to be on encryption, of course, as the enabling technology. So I'll start off with 3 scenarios for motivation of exactly what is it we want to achieve. For instance, these are just examples, but there are thousands of other examples. So for instance, you can have different banks that want to train some machine learning model for fraud detection. So they have their own customer base and their own list of transactions these do, and someone can train on that. But it would be better if they can actually pool from all the transactions from many banks together. That would give a superior machine learning model. But then again, customer database and their transactions, that's of course sensitive data, so you can't readily just share that with each other. So this illustrates what they want to achieve. So the second is sort of exactly the same, but just now in a hospital setting. So just as we heard now about maybe leukemia and cancer, but there are too few cases in any one country or any one hospital to reliably do this. But if you can merge from several countries and several hospitals, then you actually have maybe sufficient data to actually get a good model. But we have the same situation, right? This is sensitive data. We cannot just readily share medical images outside. So how do we do this then? The third scenario is different. That's on the use of an already trained machine learning model. So say there is some company that wants to automate image analysis of something. But of course, it doesn't have the means to actually have this machine learning model and all the servers that need to run on themselves. So they have to use the cloud. But then again, don't want to share the images with the cloud. So how do you deal with this? So in all of these, I'm going to explain how encryption can be used as an enabling technology to maybe overcome these barriers. But before we do that, since I'm a researcher, we have to dive a little bit into the technicalities. Not too much, I can assure you, but I'm going to teach you what is fully homomorphic encryption. That's abbreviated FHE. So we have on the slide here, if you look on the top, the plain text domain, that's where we usually are. So we have some data, we do some computation on it, and we get a result. So the computation can, for instance, be a machine learning model. Then we can do it in a more cumbersome way. We can take that data and on the left there and then encrypt it, and we end up on the bottom, which I call the encrypted domain, and that is always shaded with this purple. Then it's encrypted, but if you have encrypted with anything, if you then do computations on the ciphertext, you just get garbage. But this fully homomorphic encryption schemes, they are designed such that when you do the computations on the encrypted data, you get an encrypted result. And if you decrypt that one, you get exactly the same result you would have got if you had done everything in plain text. So this is more indirect, so to speak, but for these use cases that we're talking about, it makes sense actually this is a solution to some of the problems. So we actually go one step deeper also, just to explain how can you actually do computations on encrypted data. In reality, there are only 2 operations you can do. It's additions and it's multiplications in some algebra. So you can add ciphertext together and you can multiply them together. So this is illustrated when the computation is just a simple addition or a simple multiplication. That's exactly what you can do. But that's also all you need. Because if you can do additions and multiplications, you can actually do anything. So in a computer, at the very lowest level, we are dealing with bits, and these can be ANDed together, or they can be XORed together, and that's addition and multiplication. So anything a computer can do, you can, in principle, do in the encrypted domain then. Okay, so this is great. What's the catch? There are some major drawbacks to this. So the ciphertexts, the encrypted data, they are much larger than the plaintext. For these fully homomorphic encryption schemes to work, it has to be that way. And because of that, but also because of other things, the computations in the encrypted domain are much slower, much more heavy. So there are limits to how much you can do in practice. Yeah, so that's it. So then, we're talking about AI here. I'm talking about machine learning. So AI is bigger than that, but machine learning is a cornerstone of AI. So I'm also going to say a little bit about the basics of machine learning, or these neural nets at least. So we have seen these networks before. We have these layers of nodes, and there are edges between them, the connections, and these edges, they have weights connected to them. And training a machine learning model is just finding out how to assign weights to each model, such that when you give the input, you get the result you want or expect. We also see that there are activation functions in each node. So if you zoom in on one node, what happens in there, typically? So here we have all the inputs coming in. That's the x1 to xn over there. And we have the weights on each edge. So what is done is typically that you just take a linear combination of the inputs, a weighted linear combination with these weights. So that produces just a single number, the sum, and then there is an activation function. You apply that one too, gives an output. So there are a few variants of activation functions that are used, but the very common one that I'm just going to use for this example is this rectified linear unit ReLU, which does nothing if the input is positive, and it just zeroes it out if it's negative and cancels everything. So if you then try to do encryption, do these computations in the encrypted domain, does that work? Yes. So this first linear combination, that's just multiplications with constants and additions. Additions are much cheaper to do than multiplications in FHE. But then we have the activation function. That's more of a problem because we can only do additions and multiplications. So it has to be a polynomial we evaluate in the activation function. And this ReLU is not polynomial. It's really contains an if statement there. But an if statement, if it's less than 0 or so on, we can't use that because we can't see the values. That's the whole point of the encryption. But we can approximate it with a polynomial like I've drawn here. This red curve is a quadratic function that approximates it quite well on a bounded interval at least. So if you have control of, we know somewhat how large the numbers that come in will be, then maybe this is good enough. So it gives an accuracy time trade-off. We can approximate it even better if you have higher degree polynomial, but that takes longer time again. So this is like how it can be done. Okay, so let's look then at some of the solutions that we have to these scenarios we had, and also to what Inge talked about before. So the first one is for this scenario 3, when you want to use an already trained machine learning model, but you don't want to share the input or the output. So this is where it makes sense to do this, go into the encrypted domain and do computations there. So we have the setup here. We have let's take the hospital case, where they have maybe done some MRI scans of brains or something like this. And they want to actually, experts can study these images themselves, but having a second opinion from a well-trained neural net would actually also be helpful to have. So what happens here then is that at the hospital, you encrypt the image and you get this, just a white noise kind of picture. You send that to the cloud or wherever this machine learning model sits, right? That has maybe been trained jointly by many and is open for use for this hospital then. So this encrypted data is just fed into the neural network, producing a result, but the result is still encrypted. So whoever sits in the cloud there don't see anything. But they can still send back then the encrypted result, and it's decrypted, and then you get an answer out of this. So note that this key that encrypts and decrypts, it only sits within the hospital. It never leaves the premises. It is not shared with the cloud. That's the magic of it. So in reality, that private key that actually can decrypt these data will sit in a hardware security module, maybe HSM inside the hospital and be under control. So you don't need to trust the cloud in any way. This is like a different type of encryption than just encrypting the messages that goes in transit. The cloud never decrypts anything. So that's one solution to that. Okay, so this is like on a schematic. So what can we do in practice then? Because I said that computations in the encrypted domain are much harder. So how much can we actually do? So I took one paper to just give you a snapshot of what is actually done. So this is a paper from 2 years ago, encrypted image classification with low memory footprint using fully homomorphic encryption. Okay, so they actually do, you can classify images. And the model they use is ResNet 20, which is like a serious model. It's not like a toy. It's only these CFAR10 images, so they are 32 by 32 pixels, color images of 10 different types of objects, like planes and dogs and frogs and so on. But this can be done in the encrypted domain. So I've also taken this table from the paper and just copied that one. So in there they compare themselves to previous work, and then, but we can read off. So how well is this? Okay, so accuracy is actually quite good. It's like more than 90%. We see the memory usage on the very right-hand side is quite high. So in this work, it was 15 gigabytes to do these computations. But compares is like 512 or 100 or maybe 1, but the one with 0.8 gigabytes had low accuracy and so on. So there's a trade-offs going on here. And the runtime, 260 seconds. So more than 4 minutes to classify one picture. So of course that's very much slower than we would be used to. I mean, if you do this in plain text. But on the other hand, if you're a hospital, maybe it's okay to wait half an hour to get your answer. It doesn't. So there are applications where it's not that time critical, maybe. So okay, this is like state of the art on this part. So the next one is on the other scenarios where you do the joint training, where you want to pool your data with others without sharing it and train a machine learning model. So here we already saw a picture of federated learning, and that is a common technique to do this. That doesn't have anything to do with crypto. This is something you can do, and it's done like without any cryptography. So this is a different image of the same that Inge showed before. You train your model locally on your local data, and then you only share the model, and the models are merged. And then everyone gets back the merged model, and they can continue training on that. So this loop here should go on for several rounds. So only the model weights are sent to the central server. Yeah, so that's it. So it sounds complicated to merge models, but it's just like computing the average of all the weights. Okay, so the drawback of this is that, yeah, you don't send any private data anywhere. You keep that to yourself. But then, as also Inge mentioned, the information about your data may leak from the model you send. So when this central server sees your locally trained model, it can say, oh, you must have many cases of this and that in your data set, for instance. So. So there's still a problem here, and this fully homomorphic encryption can help solve this one too. So you can do federated learning, but with FHE on top of it. So here is like the bank example. So assume all of these banks have now locally trained their own fraud detection AI model, and they want to merge this one, these. Okay, so they do sort of the same, but they encrypt the models first. And that's just encrypting a long vector of weights, of numbers. So that's what it means to encrypt the model. So you get like 3 different ciphertexts, They send this to the cloud. We are now in the encrypted domain. The cloud will, the central server there, will merge them, add them together, and get like an encryption of the merged model. And this merged model is then sent back, and everyone decrypts that one, and everyone gets the same golden model here that is better than what they had before, and maybe then they can continue training on this, and then the whole thing repeats. So in that sense, this central server doesn't see any locally trained models, and can hence not infer anything about the underlying data. So the advantage here is that merging the models is actually quite simple. It's just computing the average of the weights often. So you just add all of these ciphertexts together, that's cheap, and multiply with 0.33 maybe in this case. There are some drawbacks. I mean, all the parties here, for this to work, all the parties, of course, must have exactly the same machine learning model, the same number of nodes and hyperparameters. And they almost share the same decryption key because they get back what they get back. Everyone must be able to decrypt. So, in particular, these parties, they want to hide their model from each other because it's the others that may be the ones they are most afraid to expose their data to. So you need extra protection of the communication maybe, that's solvable. There is also a collusion problem, so what if the central server and one of the parties actually collude? Yeah, then the central server can actually decrypt everyone else's model. So there are some issues still remaining, but it's better than just plain federated learning. Can we do this in practice? Yes, so I took another paper, also 2 years old, and just looked at what they report. So they have done serious business as well. So they've taken more than 10,000 images of brain scans, and then have a 3D convolutional neural net model to actually classify the age of patients based on the brain scan. Is what they're trying to do. And these 10,000 are then spread among several different parties, and I used then federated learning for this, but with FHE on top. And what they report is that training with encryption incurs only 7% runtime overhead. So very little overhead here compared to the using an encrypted model case. So, but this makes sense because most of the time is actually spent training locally on your own data. And then you have some extra when you actually encrypt the model weights, but there is like very built-in parallelizability in these FHE schemes. So that can be quite efficient. And the merging of the models is actually quite simple. So it's mostly the encryption and decryption of models that is extra. And 7% is like, yeah, that's doable. So I'm much more positive about federated learning with FHE on top, that can actually solve some of the problems that we're talking about today. So time is running out. So my last slide is just the main takeaways that I want you to sit with, and that's that fully homomorphic encryption can be a viable solution for problems with AI and sensitive data, but it has an increased computational cost, and that can be significant and be a barrier, actually. Yes.
Thank you, Håvard, for presenting a complex issue in a way that even I, as a social scientist, could understand. So that's quite a rag. We have time for 1 or 2 questions, if anyone has something on their minds. Anyone? Yes? Just say your name, please, and ask the question.
Hello, my name is Patricia. Thank you for a very nice presentation. I was just wondering, you didn't touch upon the intrusions and denoising or introducing the noise to the model. How is it dealt with in the encrypted domain? I mean, we know that when training the models on images, for example, it's enough to change a couple of pixels to confuse the model.
Yeah.
And I was just wondering, how do we prevent those intrusions in the encrypted domain when it's even more difficult to understand what is?
Yeah, it's so if I understand, it's not, we don't deal with that here really. So if you take an image and you have modified this few pixels you need to confuse the model and encrypt it, yeah, the model will still be confused. Because in the encrypted domain, the computation is exactly the same as it would be in the plain text domain. So if that is the case, but of course, if you don't see if you just get the ciphertext and you have to try to modify the ciphertext, then you're just gonna, you cannot do that by changing just individual pixels. So if you only see the ciphertext and you try to manipulate that, then you're gonna break everything. Then you're just gonna be garbage in, garbage out. That counts, yeah.
Okay, I have a quick question myself, because you said something about sharing the keys was a possible downside. But how secure are the keys? I mean, for me, keys can be copied and, well, they can be hacked maybe.
Yeah, of course, you have to protect the keys. So I don't touch upon that either, right? But apart from the decryption keys are crucial. If you lose them, then you lose everything. So they should be like in these hardware security models are often where they are stored. And yeah, that's a different topic actually, how to protect private keys. Yeah.
Okay, thank you, Håvard. And now we have a coffee break for 20 minutes until 11:15. I've been asked by the host here if you can hang on to your cup or glass, that would be nice, so we don't have to do it all over again for lunch and later. So there is some coffee and something to eat from the breakfast. Still leftovers, but there will be more of everything for lunch in about an hour and a half, so don't worry. Ready? All right, welcome back. Next speaker is Dumitru Roman, who's senior researcher at SINTEF Digital in Trondheim. He's going to talk to us about graph-based synthetic data generation.
Do we get it's here. All right, thank you very much. I'm Dumitru Roman from SINTEF, research scientist. I'm going to talk a little bit about synthetic data today in the context of finance, but the methods that I'll present are a bit generic, universal, and we'll talk a little bit about how we used graphs to generate synthetic data, specifically for time series data. The agenda for today, I'll try to cover 3 points. So the first one is mostly oriented towards researchers. It's our technique that we tested and experimented with in order to generate synthetic data, which is a family of methods that turn temporal, so series data into so-called visibility graphs, and then we walk these graphs to generate new time series from that walks. Then the second part is a real use case that we did with a company who is all contributed to this presentation. It's Peracton Ltd from Ireland, which is a trading company. It develops software and strategies for buying, selling equities and commodities. So we try to apply this kind of methods in the real setup, and we work together with this company. And then at the end, I will try to zoom out a bit from the data generation, the synthetic data generation problem, and try to look at the bigger picture and identify some areas where we need more work, not just on the generation, but on the whole ecosystem. So first of all, why would you translate time series data into graphs? So there are all sorts of dependencies between observations in time series that if you just look at the time series graph, you don't capture all the interdependencies. So there are some sort of connections that are hidden in one-dimensional space. So we are trying to map those observations into a graph and use network analysis graph-based techniques to try to understand connections that are hidden in this one-dimensional space of time series. Generating high-quality synthetic data time series is challenging because of 2 aspects. One is the data itself. You have all sorts of characteristics of the data that are not so easy to replicate. So like heavy tail distributions, if we talk about financial time series, so you have extreme events that occur more often than Gaussian process predicts. Then you have volatility clustering, so if you have big movements of prices, let's say, those are followed by other movements of prices. If you have a calm period, then it's very likely that the next period is also more calm. So there are all sorts of such correlations, interdependencies between data that if you generate synthetic data that you have to capture. And then other more complicated things like cross-asset movements. So if one equity goes up, then the bonds should go down in a calm market, but this is not always the case. So you need to be able to capture all these kind of situations. Now, on the other hand, you have the tools to generate this synthetic data. And these are some examples that have been used, like generative adversarial networks, Vance, diffusion models, more recent, but they all come with their limitations. So for example, GANs are known for training instability, model collapse, hard to reproduce, different runs give you different generations. So they all come with advantages and disadvantages for time series generation. So what our approach basically was to map time series into graphs, and there are different techniques that have been developed over the years, so that each observation is a node in a graph, and then you connect nodes that can see each other. So it's a purely geometrical or topology mapping. So if you think of time series as some sort of bars, you can take one bar here that connects, that sees some other bars, and you draw a line, and that's basically two nodes and a connection between them. So that's how these natural visibility graphs, for example, work, that two observations are connected if the straight line between them is not blocked by an intermediate value. There are different types of visibility graphs, like these horizontal visibility graphs that impose some rules. Like if you draw a line between two observations, all the values in between them have to be lower than the minimum of the two observations. That's more tractable computationally. And then the interesting thing about this is that you can have, if we talk about multivariate time series, you can take different time series, create graphs, and then connect the graphs. So you can capture some sort of relations, correlations between different time series. So that's the multi-layer, multi-graph approach. So this is an experiment we done. It's a paper currently under submission, where we try to use these methods, which, as I said, are not new, but they haven't been used for generating synthetic data. So the way how this our approach works is you take a time series. So you see the first picture on the left, upper left, that you have x-axis is time, and y-axis is actual value. So you have 10 observations, so 10 bars. And then you apply this natural visibility strategy that you connect nodes. So, for example, node 1 sees node number 2. Node number 2 sees node number 3. Node number 3 sees node number 4, 5, and 7, and so on. So that's basically how you generate a graph from a time series. And then each node in the graph has the actual value. So for example, if you think about prices, at observation number 1, maybe price is $120 US. So that you record as part of the value in the node. And then you can apply some sort of walks into this graph to generate new data. So a random walk is presented in the figure number 4 here, that you start with 1, then you go to number 2, then you go to number 3, and then because of this topology tells you can go to 3 other nodes. You go to node number 7, then you go to 10, then to 8, 7 again. So basically this is one mechanism to generate new time series from this, the original time series. The advantage with this is that it's traceable, so always if you generate a synthetic time series, you know where it comes from. So the number 6 at the bottom, 5, it's actually one example of generating synthetic time series, and I can trace back where and why this time series came from. So then we did some tests on financial synthetic data. So we took data from Yahoo Finance for 10 years, daily closing prices for 255 stocks for the full study. We took windows of these prices of 20 and 60 observations. Then compared 5 state-of-the-art methods like time GAN, conditional GAN, and so on. And we looked at, tried to compare with 3 criteria. So the first one was more visual, to see the overlap between synthetic and real data, so to get an intuition which method is better, which is not. Then one utility evaluation on a classification problem. So train the model with real data, train the model with synthetic data, and compare how useful this actually is. And the last one is try to compute how much time and resources each of these methods use. So this is a first comparison that we looked at. So what you see here, it's a method for mapping multi-dimensional time series data into 2-dimensional. It's called TSME method. And what you basically see here, the blue dots are the real observations, and the yellow ones are the synthetic one that were generated by each method. So what you want is that the yellow dots pretty much follow the same shape as the blue dots, and that they don't cluster, so they should intersect as much as possible. So for example, in STS method, you see that synthetic data yellow doesn't cover all the dots that you have on the blue, the real data. So that's not good. You want intermixing as much as possible. So this shows that the first 3 methods that are based on graph mapping of time series have a better visibility mapping than other methods like STS or diffusion time series. So this was more visual, is not a very precise evaluation. So in order to see if this synthetic data is actually useful, we tested on a classification problem. So give the synthetic data as training for the model. So the results here basically, so you have the graph where you have each method on the x axis, and they say under the curve how you test how good the models are on the y-axis. The red ones are the graph methods, whereas the gray ones are the generative methods, and the VRP is the method where you just shuffle the original data. So it's kind of serves as the baseline. So consistently, the graph methods are much better than most of the other generative methods as per this graph. And on the right-hand side, we see also how much time it took to actually generate this synthetic data. All these neural network-based methods, they need a lot of training that you basically don't have to do with these graph-based methods that we devised. So what to take from this is basically that this topology does the encoding of the different relationship between the observations. Then the metrics that we used are the relevant ones, and basically we see that you can use simpler methods than machine learning to get some good results. Also in terms of speed, this matters a lot in practice. But of course, there are limitations here, like we can only generate synthetic data of the values that have been seen in the real data, so extreme values are not captured with this. So rare event generation still needs dedicated design. So then we tried to use this on work with a company on a real problem in the trading domain. So there are lots of problems in the finance domain when it comes to data, like internal usage restrictions. You can't really share the data. There's not enough history at the right granularity, like minutes or even seconds. If you look at trading, very often all data becomes irrelevant, and so on. And there are many cases in finance, like anti-money laundering, customer journey analysis, payment flow, anomaly detection, equity and futures market where suffer from these problems on the left-hand side here. So if you want to use real data, you have several problems: finite coverage of different situations in the market, like liquidity crisis, volatility explosions. You have the sampling problem and survivorship bias. Many data sets are filtered or incomplete. You can't really access a lot of data. It's expensive, licenses, what you can do with them, and so on. So if you really manage to get good synthetic data, you will overcome a lot of problems in this field. So if this company that we worked with needed synthetic data for better trading strategies, but they needed to overcome this problem. So the statistical data is to have the fidelity attribute. That means that, for example, return distributions, volatility, clustering, heavy tails, skew kurtosis have to be within the certain ranges. Same for temporal dynamics. You have to capture dependencies across intraday, daily, and longer horizons, and so on. So there are many requirements that they had for ensuring that this synthetic data is actually usable. Where synthetic data comes into use, it's in several stages in trading. So in trading, you have a process. You have some ideas, make some hypotheses, collect data, try to get some signals. You develop a model. You backtest on historical data to see how your model would perform. You go into production, check that it's robust. You start with paper trading, so kind of fictional trading. If it goes fine, you go live trading and try to make money. So synthetic data basically cover these steps of data engineering, signal engineering, and model training. So this was a kind of commercial type of applications where we took 1 year of commercial minute bar futures data, so certain type of financial products, and we ingested this data. We mapped it to the graphs as with the techniques I introduced earlier. We generated synthetic data by walking these graphs, and then we rejected data that was not within these constraints that needed to be satisfied for synthetic data, and then generated the data. So these examples of 30,000 years of synthetic data for 3 types of future commodities contracts. From those, we took some samples and calculated all these properties that to check that we satisfy the constraints on things like mean, standard deviation, skewness, but also on Pearson. So statistical characteristics of the synthetic data. Then basically what we did with this synthetic data, we applied it to a trading algorithm, a trading model. We trained that model that was trained originally on real historical data, and we tried to see if by adding this synthetic data, actually you could increase the return of on investment. So by using this synthetic data, they proved that you can get a 2% increase on return over a certain period of time. And on the right-hand side, you see a screenshot of the product that they developed around this. So really, it can have some real value using synthetic data. There was some validation in the process. I don't have time to go into much details here, but we looked at performance metrics, distribution analysis, out-of-sample testing, data quality, and explainability of synthetic data. Now, would you put your money on such strategy based on synthetic data? Well, not really. There were various aspects that you need to overcome in order to really use the synthetic data at scale. So first of all, is actually the scale. It's a lot of data that you can generate. You need to store. You need to analyze this data in one way or another. So it's a big data kind of problem. Then once you have the data, there's the question is how good is this synthetic data? So you don't really have people how to assess whether this fake data is actually satisfies things. It's a bit of blurry area that you don't know how to approach. Even basic things like visualizing this 400 time series to analyze them, just visualizing is a problem. Then you have other problems that we didn't look at, like extreme events. Each separate stock or equity has different sort of KPIs. So how do you operationalize this whole process? So this brings me to the last part of my presentation, which is trying to cover not only the generation problem. That's one aspect in many other aspects related to synthetic data. And the question is, how can we cover this whole life cycle of synthetic data and also expand it to not just time series or just text, but making it in a multimodal context. So typically a full life cycle, you have some real data that you take as basis. So you need preparation of the data to fix this real data. Maybe has gaps, maybe certain statistical properties are not good. So you have the preparation stage where you work with the real data. Then you do the generation with examples like the methods that I showed earlier in the presentation. But then you need to spend a lot of time on, is this data good for my purpose? So assurance of the data, how do you evaluate, how do you benchmark this data, how you mitigate problems in the synthetic data. Then once you have this synthetic data, you have to make it available. So how you distribute this data. Kind of think of some sort of can be marketplace of synthetic data sharing, but then you have to actually put it in existing processes in real pipelines. So that's deployment, and you also have a lot of compliance problems in this whole process. So what we did is try to define each of these stages of the life cycle. Won't go into much details here, different types of problems that you have to address. So we argue for a sort of ecosystem for synthetic data generation tools and approaches for each step, and involving various types of stakeholders, not only data scientists, but also things like domain experts, product owners, and so on. So to zoom even outer, how can we do this for different data modalities, not just time series? So we looked at text, images, audio, video, time series, graphs, and tabular data. We tried to work with different domains like multimedia, finance, cybersecurity, and so on that have these problems. And we defined some sort of research roadmap where we need more work like cross-modal coherence, rare event synthesis, provenance, and lineage, and so on. So I guess I'm getting close to finishing. Just a few messages. In our case, basically topology is enough, so working on translating time series using graphs, no fancy machine learning or deep learning algorithms. Speed is very relevant in practice, so if you work with a real-world problem, you can't wait days to train a machine learning model that may not perform as good as more like deterministic approaches like the ones with the graphs that I mentioned here. We have seen potential measurement, clear added value benefit for practitioners, like this company that we work with. And also we argue that generation is not one single thing, but has to be seen in a broader life cycle of synthetic data generation. So last but not least, I'd like to invite you to an event that we are organizing in Oslo. It's called Data Week. It's basically supported by Big Data Value Association, where SINTEF is a member of. It will be in May. There are many data-related sessions, so I hope some of you can make it there. Thank you very much.
Thank you, Dumitru. I just signed up for Data Week, so I'll be there. See you in Oslo. We'll go right on to our next speaker, Tom Michael, who's professor at the Computational Biological Unit at the Department of Informatics here at the UiB. Tom is going to talk about opportunities and challenges for learning disease mechanisms and risk prediction models from population-based data.
All right. Thank you very much, Doug, for the introduction and for the opportunity to speak here. So Inge already gave a very nice sort of general overview of the challenge of working with synthetic data, genetic data in particular, which is what we are working with. Just to give a little bit of background about myself here, I'm really a computer scientist, so the thing that excites me are sort of mathematical and computational problems that arise from working with complex biomedical data. I'm never involved in any sort of data generation or study design or all the kind of questions where all these ethical approval procedures come in. I'm just someone who wants to respect all the rules but not have to worry about those things. And so what I'll talk about today is not so much about actual science, but more some practical experience. What is it like for, say, computer scientists to work with sensitive data? And some of the different solutions that Inge already mentioned, and how does it feel like? Now, one of the problems of getting a bit older is that you develop some memory about the field, and it's harder and harder to get excited about the next new hype. So we're talking here about challenges of working with sensitive data, and that reminded me then of some quotes here. So basically, the only message that I want to bring today are these two quotes. So we can read them. So first one is 2010. Among the most pressing challenges of working with sensitive data are data transfer, access control, and management. And then they propose a nice solution, that one solution is to house the data centrally and bring computing to the data. So rather than a researcher downloading data, you actually bring the compute and the scientist, or the machine learning scientist, to the data. Similar point was made in the other paper, 2011, again, 15 years old. Cloud computing may allow access to data in a more controlled fashion than the current practice of downloading and computing on large data sets. So in a way, I could stop my presentation here, because that's really, I'm just going to make the same points that these people already made 15 years ago. But that would be a little bit boring, so we'll just continue. And I'll give you just 3 examples that are a bit on different scales and using different solutions of 3 projects that I've been involved in. So one is a project that was funded by the Research Council of Norway. It was mainly about developing computational methodology, but then also involved some applications on real-world data, in particular some data from a population-based study in Iceland. The second project is part of a larger European project involving several partners. And I'll particularly talk a little bit about working with data from something called UK Biobank. I'll introduce what that is later. And the third project is a project led here by the Department for Epidemiology, funded by Trond Mohn Foundation, about understanding cancer risk in women and using population-based registries. So it's kind of 3 different scales and 3 different types of challenges that we encounter there. All right, so let's go into the first project. I don't want to sort of say too much about the details, but The main thing here, this is a study from a bit more than 5,000 older individuals. There's lots of, basically anything that can be measured about those individuals, about their health status is available. We're particularly interested in their genetic data, as well as some measurement. So it's blood measurements, but it's not your typical blood analysis. In this case, they measure up to 7,000 different proteins, so different molecules in a blood sample. So obviously, this is what one would categorize as highly sensitive data, so it's not something that they could just say, here's the file and do what you please. What we're interested in is basically, without going again too much into detail, is combining these genetic information with then more this information from the blood sample and building models, ideally models of sort of causal networks. So we try to understand what are the causal relations between, say, one protein going up and other proteins going down. Ultimately, to understand a little bit more about potential underlying mechanisms of different diseases. And then we link those models to various clinical outcomes. In this study, we were interested mainly in future heart attacks. So we looked at blood measurements at one time point, and then checked whether these were predictive of individuals being at higher risk of having a heart failure later in life. And then by linking these two steps, you can sort of start to hypothesize about what potential molecular mechanisms might be there. Like I said, I mainly want to just explain how the practicality of working with this data went. In this case, it was super smooth. So this was with colleagues at the Icelandic Heart Association, and here the model implemented was exactly what was recommended in these quotes from 15 years ago. Namely, they didn't send any data to us, no data ever left Iceland, but rather we and the compute came to the data. The way this worked is that there was a researcher employed on the project here who was simply provided with remote access to their servers. So they did not only provide the data, but also provided all the HPC infrastructure to actually analyze the data. And this was very smooth, so it was only a letter of intent, collaboration signed between universities. And then because this was a new collaboration, they sort of insisted or said it would be a good idea if the researcher visits us for, in this case, 3 weeks, both to do some practical things and simply as a confidence-building measure that we get to know each other personally, and then we can let you work with the data. And everything else was done remotely, simply to remote access to their infrastructure. This has been a very nice collaboration, and we're planning future projects again. So this is an example where if you bring compute to data, it gets very easy for everyone. For us, there's no problems with where are we going to store all this sensitive data, how do we bring it into Norway, what are the constraints, how can we set up the compute there. From their side, it's very nice as well, because they still control their data. So they don't have to worry about what happens if we send those files to those people. Will they analyze them in the way that was sort of approved in our ethical approval, et cetera, et cetera. So they keep control of their side of the project, and we simply can bring in our expertise without having to worry about these sort of practical details from our perspective. So that's one example of bringing compute to data. Second project is a larger European project, but it's again relatively similar. So here as well, we want to understand disease mechanisms, but also build new risk prediction tools, finding ways to group patients into sort of different categories, and potentially also build resources for drug prediction. And again, it's related mainly in sort of applications on heart disease. And again, it involves a lot of different types of genetic data and this kind of protein level or metabolome level, sort of very detailed data about a person's physiology, so at the molecular level. It's a project that involves multiple partners, so that gets into, again, one of the issues that Inge mentioned about how do you combine things from different institutions. So the way it practically goes here as well, luckily we can mostly work in this model where we bring compute to data. So with several of these institutions, we have similar kind of partnerships as I mentioned before, so where we get access to their servers. At this point, we haven't reached where the question of how do we actually integrate them, so there's really challenges with each and every data set individually. But the setup is roughly the same as what I mentioned in the first application. What I want to highlight here is, as part of this study, we're also working with data from UK Biobank, and this is, I'll give some more details later, but this is really the world's most sort of comprehensive data set on all aspects of biological health, lifestyle information. Amazingly, it's available to everyone worldwide as long as you do health-related research on it, and the access is via a research analysis platform, so a cloud computing platform, and so I'll show you how that works. A few words about this UK Biobank. So it's an amazing resource. It started in 2006, and data has been collected on 500,000 people. So it's mainly, they're interested in sort of the onset of age-related diseases. So the people recruited were middle-aged and living in the United Kingdom at the time of collection. And there's pretty much everything here. So here in the visual, you see everything. There's MRI images, there's sort of tissue MRI images, there's physical activity monitoring, there's lots of environmental factors. For instance, do you live in a deprived area? Do you live in a rich area? How far, say, are you living away from parks? What is the air quality there? There's obviously all the genetics is there, similar as we talked before. All these kind of protein measurements are there. So it's an enormous resource, obviously extremely sensitive data, so this is not something that you suddenly want leaked out into the public domain. The access to this data is incredibly easy for someone like us, so when we're mainly interested in doing computational analysis. So they work with access management system. There's a bunch of compulsory training that you need to do before you can do anything there. And then the application form is like a dream. So there's a 200-character title. There's 2,000-character outline of your research. And then whenever you click yes here, you need to explain how is it related to health. How are you doing health-related research? Is it in the public interest, and are there sort of potentially contentious outcomes? So it's very smooth. It takes maybe a day to fill in, and then you're done. And then it typically takes about 3 months. So the project is reviewed, then an MTA needs to be signed, so you involve the legal department, but everything very easy. You get access for 3 years, and then you pay a fee depending on what level of data you want to access. If you want to access everything, it costs you £9,000 for 3 years, so very reasonable, very easy to get access to. So all the kind of things that Inge also mentioned, we need to have more opportunities for AI, ML on this type of data. This is very smooth and how it should be, in my opinion. Now, amazingly, or somewhat not, so if you think back about these quotes from 15 years ago, actually until last year, UK Biobank was still operating with this data download model. So if you got access to this data, basically you could download genetic data on 500,000 individuals, which if you think about it is quite crazy that so many people across the world could download this data. Of course, you sign up that you're going to follow all the strict protocols of protecting that data, but from the perspective of UK Biobank, once you give the data away, the only thing that is left is trust that people will actually do this. And in 2004, actually, then they switched. They switched now to a computer data model. So from then, or since then, it's no longer allowed to download any individual level data from UK Biobank. Instead, they have launched this research analysis platform. One motivation had to do with the scale. So the scale became so enormous that practically it was no longer possible to download. But also, if you read their motivation, it's about greater security and obviously control that can be assured with downloaded data. So they, of course, need to justify everything they do towards the British public. 500,000 is a huge amount of data. And this is part of their motivation here. And how is this done? So it's operated by a company and using kind of the typical Amazon Web Services cloud computing. And just to give some numbers now, there's more than 30 petabytes of data there. About 15,000 researchers worldwide are working on the data, and about 11,000 projects are being done. So the scale is absolutely humongous, I would say. And working on this platform, if you're a machine learning scientist, it's absolutely a dream. You get your data, everything is de-identified, they take care of that, you don't have to worry. Data is just there. And then it's the standard thing if you've ever worked with Amazon Web Services. So you want to run an analysis, you simply launch the virtual machine that you need. If you need big analysis, training some models, you launch something with all the GPUs you want. If it's just a standard analysis, you just start with a normal machine. So it's very easy, and the prices are quite reasonable. So it's your typical Amazon Web Services cost without sort of any markup or anything. And moreover, they do not charge for any data storage of UK Biobank data itself. If you upload additional data that you want to analyze kind of together with UK Biobank data, you pay a storage cost, but the UK Biobank data itself, the storage is for free. All right, so this was UK Biobank, this huge population-wide registry with absolutely fantastic way of accessing and analyzing data. The last project I wanted to illustrate is a project that started, or should have started, I should say already, if I kind of preempted my next slide, about 2 years ago. And this is about a question about identifying potential causal mechanisms for cancer, a relation between sort of the pregnancy factors and a woman's reproductive history on future cancer. So these associations have been found in population-wide studies, but why we see this relation is completely unknown. And so the idea of the project was to use various types of Norwegian registry data, use again kind of methods for learning causal models together with machine learning, and then hopefully ultimately be able to inform new cancer prevention strategies. So here, unfortunately, or just one slide in between, so as already mentioned by Inge, access to that type of data is obviously governed by lots of laws and regulation, as it should be. If you apply for data, you need your ethical pre-approval, but crucially, the health data services still work with a data download model. So once your study gets approved, you actually get all that registry data on your server, basically on your servers, and it's your responsibility to then treat it according to all those rules. And as they say themselves, important points in the data access application, so obviously there's the things you need, but also they are, of course, concerned where will you store the information and how is the data actually going to flow. And that's, of course, coming from the fact that you actually download the data and you have to handle it, and they kind of give up their control. So what has been the timeline of this project? So as I mentioned, the ethical application submitted now almost 2 years ago, approved a few months later. Application was sent to the health data services here, October 2024, and there is still no data for the project. The reason is that of course, there's a certain time that it starts for them to process the case, but in this case, the way they framed it was a partial approval. In practice, the partial approval means it's difficult to execute the project as it was planned. So the partial approval pertained to that, yes, we want access to different registry data, but they do not allow the linking of these individuals in the different data sets. And if you read their communication, the concern is really about, on the one hand, that they say machine learning has not been done on this scale across this many registries. And they see a lot of concern or risks for that potentially identifiable information might be leaked, and how does it sit in these models? So some of the issues that Inge also highlighted. But then also, if you read their justification, you say there's a lot there that relates to who will get access to that data, how will you maintain the security. So a lot of the questions relate, again, to the same problem that the data is actually getting out of their control. And so basically, we're now here a long time after the ideal start of the project, and the project cannot be done because the data that was requested is simply not becoming available. So that's kind of, I get to the conclusion. So this is, I've given you 3 projects. One is like a small scale where you interact directly with a partner institute, where it's relatively simple to set up this remote access. The other one was this UK Biobank, where it's population-wide, but it's still a study, so people were enrolled in that study, gave their consent for the analysis, etc. And then you finally get to like the bigger scale, where it's data on all of us that has been generated. Nobody was asked explicitly to what extent we want to be involved in research. So that's kind of the next level problem. But at least from the perspective of someone doing machine learning or data analysis in general, or I should say maybe my personal perspective is that it's vastly superior if the compute can go to the data, if we as researchers can go to the data rather than us having to download the data. So this works very well with individual partners, but it's still not a very common approach. UK Biobank, I would say, is absolutely gold standard. And maybe a model like this might also help for the Norwegian health data services to maybe maintain control while allowing still more AI-based analysis. So I'll end up again with the same quotes that I started with, and would argue that many of the problems we discussed today have been identified 15 years ago, at least in the field of genetics. Solution, at least I would argue, partially exists, but what we are still lacking is more implementation. Thank you very much.
Thank you, Tom, for a very clear and convincing message. Bring the computer to data, rather than the other way around. It's easy. Our next speaker is from, is a data engineer at Vipps MobilePay. Alex Teodosiu is, he will talk about a payments journey, ethical AI and sensitive data. I'm looking forward to this because I've used Vipps a few times. So.
Thank you for having me.
Coming over.
Yes, thank you for having me. Like you said, my name is Alex. I'm a data engineer at Vipps MobilePay. So when building analytics and AI on top of sensitive data, it ultimately comes down to trust. The trust of the user who expects privacy, the trust of authorities who expect traceability and compliance, and the trust of our business processes that expect to rely on our data platform, oftentimes in real time. So in this talk, I'll be speaking about how we engineer that trust by taking you through a payments journey. A bit of context before we start. We have 12 million active users across Norway, Denmark, Sweden, and Finland that contain a lot of sensitive data about authentications, logins, addresses, and so on. 500,000 shops, and over 1 billion transactions a year. The transactions themselves also hold sensitive data like payment message and indirectly the cards and accounts of the senders and receivers. So what happens behind all of these transactions? Simply put, the sender will Vipps money, it will get processed by a few servers, and then sent out to a shop or a person. In some cases, Olga, our anti-fraud machine learning model, will block a transaction. There's a lot to unpack here, so the agenda for this presentation is that we'll start off with how it's ingested from the different application databases into a central data platform where metadata, labeling, proper cleaning is done so that it can then be used for analytics within the company. Then we'll speak about how it's used to train our machine learning model and the caveats around the data. And finally, we'll speak about public sector reporting and how this is aggregated and how this data can influence policies and ultimately help the end consumer. So there are a few constraints around the lawfulness of processing data on the basis of contractual obligation, consents from the user, public interest, and so on. And that's the basis for our constraint space. We also need to prevent misuse and mishandling of data, both intentional and accidental, and support AI, machine learning models, but also recently LLMs, and build that on top and give it the proper context in a secure manner. And our way of doing that and addressing these constraints that pull in different directions is through a governed data platform. So on one end, you have tons of data producers. These are different software product teams that have data in different databases across the countries for the different products and in different formats and structures. And these all need to be brought in one place so that it can be governed properly. Then it gets ingested, it goes into a landing zone, an ADLS2 storage account in Azure, Azure being an American company, but all of the resources, compute, and storage resides in Europe. Then we use Databricks to relationally interact with the physical storage layer, where we have a medallion architecture, we process this data, and we'll have selective replication of data across Databricks workspaces. And it will be consumed by a variety of different consumers like dashboards, machine learning models, automated reports, and so on. And what's important here is that this data cleaning and governance is done once in the data platform, and we're consumer agnostic, so it can be reused in many different places. And the data platform, from a governance perspective, needs to answer three very important questions. Who gets access to the data? What data do they get access to? And why? So to answer these questions, we look at it from the lens of roles this time. You can think of the data platform as a marketplace, an internal marketplace within the company, where there's essentially two roles. On one end of the data platform, you'll have the data producers. These data producers give us data, and they label it, if we can call it that, in an integration configuration, which is a data contract as code, where they'll give us service level and governance level metadata. We're in the middle of the marketplace. We might join a few data sources together, do a few things, and then we give it to data consumers. These data consumers can access the public data sets, so public within the company, that do not contain sensitive data without any friction. Or if a data set is labeled as sensitive, then they will access it through a purpose-based analytic project. So let's dive into the details of how this is done in practice by starting with the integration configs and the metadata that we get from producers. So there's two types, essentially. Service level metadata, which is just there to manage expectations. You'll get information about the data, about the software team that owns the integration, which is important because these data sets will transfer hands and many times throughout the pipeline in the organization. And then some contact information so that we can respond to incidents quickly, and service level metadata, which is important to mitigate the critical use of unreliable data. So they'll tell us whether a data set is reliable, how often it's updated, and so on. Then there's governance level metadata, quite important for compliant use. So the producer will label it, whether it contains PII or sensitive data, and then label the columns that contain that data. They'll manage availability, whether a data set is public or sensitive. If it's public, they can mark it there already, and then it reduces friction down the line. And in some cases, we might even clean and desensitize this data as early as this point in the process. Data modeling could be a presentation of its own. I think it's super important. I might be a little bit biased because I'm a data engineer, but what we do is we follow domain-driven modeling, where the main high-level domains like users, payments, merchants, are modeled within their self-contained domains. And this is very important, for example, to help us with GDPR deletions. So all user data will be in a domain, and the payments domain will not carry any sensitive user data in their events. That way, if we need to GDPR delete a user, we only clean it up in one place, as opposed to going through this humongous model of payment events. will clean data and standardize it across these different data sets, anonymize user IDs by hashing them, and then label data as we're joining as sensitive, but also label the relationship between the data sets and some column-level descriptions to give context to LLMs that are built on top of this data. Now, it's very scary when working with LLMs because we don't want to give access to personal information. And so how do we make sure that they only get the public, non-sensitive information? We do that by physically separating a PII model with sensitive data that then gets funneled down into a public, non-sensitive model where we drop the columns that are sensitive, and that further gets filtered into a model that aggregates these transactions, let's say daily. So continuing on that concept, we have persisting metadata across the layers. So we got metadata from the producers, we're now transforming it. Let's say we're joining multiple sources. We take the highest level of severity on the hierarchy, and that takes precedence when we're building a new model based off of multiple. But still, even with these data modeling principles, it gets complicated very fast. As the organization grows, there's more data sets, and there's new schema definitions, new versions, and we can lose track of the data that we have within our organization. And that's why cataloging and discoverability is such an important theme, because you cannot control and have proper governance principles over what you don't even know you have. And this is a recurring theme that I've seen in the previous presentations, where you'll have a metadata catalog basically stating what you have in your data sets and models. So we'll have that, the metadata catalog for all of our models across all layers. But for the, let's say, gold layer that we actually expose to data consumers internally, we will have a dashboard where you can have an extensive list of all data sets, what domain they belong to with domain-driven development, and whether risk and compliance approval is needed. So let's say you have a data set that you found, and it's needed that you get some approval by someone within the organization. Then you create an analytics project that is purpose-based access control. And here, thinking back to the initial 3 questions of who, what, and why, you'll have a data consumer who needs some data, as opposed to getting permissions on the basis of their role, like in role-based access control. In this case, they create an access group with other consumers that are involved in this project. Could be people, could be software services, and that's the who. For the what, we have what data sets they need, and then continuing on data minimization, specifically what columns they need, because they might not need all the columns within a data set, and we don't want to give them all of that. And then for the why, they stipulate the purpose of the project, the duration of the project, how long they need it, and this then gets approved by our legal department. One of the very interesting data consumers is Olga. Olga is a real-time anti-fraud machine learning model whose responsibility is to block a transaction if it's suspected of being fraudulent. In this case, our 2 brilliant data scientists, Ivan and James, who developed this model, will create an analytics project where they state the purpose and the access data related to logins, authentications, user event history, transactions over time, in order to train Olga. But even with this data being cleaned, they still encounter problems because of the nature of the data itself. They notice that there's a massive imbalance between legitimate transactions and fraudulent ones, where there's millions of legitimate transactions for each one fraudulent one. And this is a major class imbalance that can be solved by either upscaling the minor class through, let's say, data synthesization or other methods, or downscaling the major one. So the fraudulent relationship assumption that Ivan and James thought of while developing the model was that all transactions between a sender and a receiver, where one of the transactions is fraudulent, should also be marked as fraudulent. So that way they can upscale. That assumption ended up being false, because there are some cases where you have extensive history with someone and the last transaction was fraudulent. And that assumption baked into the model in the initial development and caused errors. So when we're dealing with synthesization of data, we need to be careful because we bake those assumptions into our models. So we see that data quality beats model complexity. We have real-time constraints where it needs to happen in less than 500 milliseconds because when you VIPs, you expect instant transactions. So that decision needs to be made fast. In addition to that, Norwegian legitimate user behavior might be different from Danish legitimate user behavior, and it might also differ by product. So that also needs to be split out. And coverage is more important than perfect accuracy. We don't necessarily need to block every transaction, and also in doing so, we might end up blocking transactions that shouldn't be blocked, which lowers user experience. But we want to have a broad coverage to remove incentives from fraudsters. So simple, fast models are important, splitting data by market and country, and using high-quality data over model complexity, because then it would be difficult to get it in real time. Pre-computing and aggregating features is a must when dealing with real-time solutions. So having these in an online feature store that could then be looked up on inference time is absolutely necessary. Ivan and James went for a supervised learning approach with decision trees. And then in terms of the compute, it's deployed in Kubernetes, and you have each component, let's say, for simplicity, a component in each country that can scale up and down individually. For us, cold starts are not an issue because we have transactions coming in 24/7. So let's see how Olga can be a data producer. So far, Olga receives payments, it approves payments or rejects them. The thing that happens when they reject a payment is that we cast a shadow over what that payment could have been. We don't know if it's fraudulent or not because we don't have the counterfactual of what would have happened if we let it go through. But we do, however, still have some information that we get. For example, we can get disputes on approved payments. In this case, we add to the data set that's already pretty small of fraudulent transactions. Or we can get customers contacting us complaining that their transaction didn't go through, which gives us information about false positives. So all of these stopped payments, these disputes, these customers' complaints can go back into the data platform, this time with Olga being a data producer, where they create an integration configuration, metadata, and so on, and then it goes back into the platform, and it can then be used in many other places. Olga ended up being a good success. In April 2024, at a peak, we had 6.4 million Norwegian kroners in fraud, and in the same month of the following year, we had 64,000. Now, for the final theme, it's public sector reporting. We have police reporting, where the police will ask information about a specific individual, where they have a court-approved document that they say they need information about X person. So we give them granular information about that person, and we have a time-sensitive SLA with these law enforcement authorities. So we need to automate these processes as fast as possible, which is another important aspect of a data platform. Then we have tax authorities, where we give high-level aggregates about different things. Here again, sensitivity is not an issue because of how much we're aggregating, and we're not aggregating on the basis of something like a sexuality or anything like that would be sensitive. And then finally, we have central banks and statistic agencies that are interested in general trends in the digital payments market. They're interested in economic indicators, so how different products specifically are performing. And we need to make sure to not have any personal identification information or any mapping to one specific person. So let's take an extreme example of a postal code where there's very few people, maybe 10 people, and only one of these people is over the age of 65. So even though we're aggregating based off of that, in this example, you can directly identify that one person. So those are things that we need to be aware of when aggregating and giving out to the public. And this shapes policies. So for example, the Danish National Bank in Denmark had 4 strategic focus areas, and some of them being based off of the reports that we give to them. Of course, we're only one small part of a larger ecosystem, but the reports that we give help shape policies. Another example would be payment infrastructure. So digital payments have different infrastructure than, let's say, traditional card rails. So knowing how much digital payments are increasing, whether it's with accounts or with cards, with other stuff, we give them information on where to focus and where to guide their attention for the next year. Then there's fraud patterns as well, knowing which demographics and age groups are affected by fraud, how much is going up and down, those types of things. And an interesting example would also be coronavirus. So during COVID, we gave reports of usage segmented by age groups. And then that potentially joined with some other data sets like healthcare or something else could give governments information about what demographics are the most at risk of using cash instead of online shopping, and then contracting and spreading diseases. If there are some takeaways, it would be that governance starts at the data platform and not in specific analytic projects. Data platform needs to really be baked in from the very start of our analytics process, instead of being done individually in many different places. The answers to our governance questions of who, what, and why is metadata, metadata, metadata. It's so important to have an overview of what we have. AI thrives on well-structured foundations, and when creating synthetic data, we need to be careful about the assumptions that we make. And finally, a robust data platform is more than just technical. It's a social obligation. It helps drive policies and ultimately ends up helping the end consumer. Thank you.
Thank you, Alex. And we have time for maybe 1 or 2 questions. And while you prepare questions, I just wanted to say that I think I was flagged by Olga once. Because really? I was doing this charity event for Ukraine a couple of years ago, and for about 40, 50 people came. And the typical donation was something from 200 to 500 kroner. And since people don't carry cash around anymore, most sent it by Vipps. And the next morning, I had an email from my bank saying that my account was closed until I could explain how I had all this money in my account. And they turned out, I guess I triggered some kind of drug dealer profile or something, because that's what these amounts are usually user doses.
You should create a customer dispute so that we can get the false positives.
Right. So any questions, comments before break, before lunch? People are hungry. Alex will be on the panel also after lunch, so we can continue the discussion then. Okay, one here. Sushma.
Thank you very much. This was really interesting. I can see so many parallels between what you have been thinking about and how you design these efforts to how we consider and plan for data in academia, for research questions, for example. So I'm wondering whether there is a way for public-private partnerships to thrive in Norway. There is a lot of information here. We don't need to rediscover all of this or reinvent all of this for ourselves. Have you thought about it as a company that also puts social responsibility as one of their cornerstones in can we reuse this knowledge and can we develop these partnerships into the public domain?
Yeah, that's a very good question. And I think this seminar is actually an example of that, where as a private company, we want to share what we're doing in order to enable private sectors, but public sector and research sectors to reuse some of the same components. In terms of sharing data sets specifically, I don't think that will probably ever happen, at least not anything that's sensitive. But in terms of processes, there's definitely a lot of sharing to do, yeah.
Okay, thank you. Then we have lunch, and there is some sandwiches back here. There is some gluten-free, there is some without meat and fish, so help yourself, and be back here at 1 o'clock sharp, we'll start. Det er en sånn klikker der oppe som du kan bruke til. Ja. Det er en sånn. Welcome back. I hope everyone got some carbs and coffee in their stomachs, and some. I heard the conversation was going lively here during the lunch, so that's good. Our next speaker is Erik Gundersen. He's a section leader in the Norwegian Cyber Force and also associate professor at NTNU, and he's going to talk about military-grade data. And a little fun fact here is that Erik is also from Tromsø, just like me, so I expect a brilliant talk today.
Thank you very much, Dag. So, first of all, I've been to Bergen several times. It's always been wonderful weather. It's not what I've heard. And then I told the taxi driver, she told me, don't tell anyone. Then we get more people here. So my mouth is shut. Okay, so I've been working with AI for some time, and I did my PhD in 2014 in AI while working in the industry. I did my master's in 2004 in AI, and I worked with developing commercial AI software since 2006 with Tore, who's here as well, among one of the companies I worked with. Today, I'm in the armed forces, where I'm not a section head, but I'm principal AI advisor in the newly founded Center for Data and AI in Norwegian Armed Forces. Today, I'm going to talk about military-grade data. So, what is it? It is hard to get. That is what it is. For several reasons. So, data is collected remotely in the military. Sensors are put on ships, on planes, on vehicles, on drones. Soldiers carry sensors with them and put them out in the terrain. They are on bases, they are on outposts. Sensors even move. That is one of the problems we have. The data is collected in harsh conditions. Weather change. Well, you know Norway. Weather change all the time. It's cold, it's windy, it's wet. Sometimes it's even warm. And the military operate outside, in the forest, on the mountains, underwater, in the air. Very different conditions. The hardware needs to be rough. It needs to endure these harsh environments. It is also operated by novice personnel. And the data needs to be collected in these conditions as well. It's a high volume. We have lots and lots of sensors. And we don't only have text or images. We have videos, we have time series data that might be high frequent and updated in real time. So collecting and transmitting this data becomes important, but because of the size, it needs to be handled on the edge. So we need edge computing, something I hadn't thought about before I joined the Norwegian Armed Forces. Okay, that is actually a thing, not only in research papers. The data could be behind enemy lines. And this could be deadly for those who collected data, because transmitting the data becomes dangerous. So you send data, your enemy might know where you are. And when your enemy knows where you are, you have a problem. Military data is not only hard to get, it's hard to use. It's high variety. I said we have many different sensors. We have different types of data. As I said, not only text, images. And interpreting this data and understanding the patterns in the data requires deep domain knowledge. Many sensors aren't standardized. So even if you have the same type of sensor, you have different types of data coming out from it. And then we need to transform it. Data is not shared in a standard way. There's a distribution shift in the data. Our data comes from the real world. The real world changes all the time. In Ukraine, they detect 12,000 new targets each week, and they annotate this data. And it's from film, so it might be 10 to 100 annotations per detection. And new assets enters the war all the time. The war in Ukraine is a war on innovation. Drones are being used, they are being built, custom made by the forces, so they change how they see all the time. How they look and their form, colors, everything. Ground vehicles change. And this innovation for drones, the innovation time is 6 weeks. This means that for every 6 weeks, you have to innovate. If you don't do that, you're not competing in the same game anymore. So everything changes all the time. And your enemy tries to fool you. They try to break your machine learning system. So there's not only a distribution shift, it's something I call adversarial distribution shift, because they want to fool you. And putting a cage on the tanks, as here, might fool your system. And then you have a problem. And if that wasn't enough, data is hard to share. So, to get access to data, you have to be authorized. And there are different levels of authorization. You have confidential, restricted, secret, top secret. And all of these authorization levels, they have their own network, because we cannot share the data on the internet. It's not enough to restrict it and put it in a net. There is a closed gap between the internet and our data. So it has to be put on own computers. So it's a restricted network with restricted computer handling restricted data. There's a secret network with secret data, secret computers handling this data, and only the people that have this authorization level are allowed to handle the data or to use the computers or use the network. So, it means that for us to collaborate with someone, you have to be authorized. And to be using the data that we are using, you have to be authorized at this level. Getting the authorization in Norway now takes 1 year to be authorized as secret. It's a huge waiting time to get authorization. So for us to share the data, it's not easy peasy. It's a problem, I'd say, and it's one of the many problems that Norwegian Armed Forces Center for Data and AI are managed to try to solve. And that is what we're doing. So I want to tell you a bit about what we are doing. So we are a center, we are newly founded. Our goal is to make AI work in the Norwegian Armed Forces everywhere, to operationalize, get AI used in every part of the Norwegian Armed Forces. We are going to get effect out of it and value out of it. This center was launched this year, January 30th. And lots of stuff is going on already. And it has been also in the Norwegian Armed Forces for a long time. We have our own research institution, the Norwegian Defense Research Institute, FFI. We are partners in research projects, the AI centers, and we've been partners in research projects for a long time. But we have the same problem as everyone else. There are lots of research, lots of development, lots of innovation and prototypes, but getting them used, operationalized in the Norwegian Armed Forces is really, really hard. And this is our task. There's this valley of death there, you see, between the research and operative capability on the right-hand side. This is where good research ideas and good products go to die and not be spread and used in the Norwegian Armed Forces. This is recognized, and our goal is to take these ideas, find the valuable ones, and put them into use, good use for us. So we're going to scale the research. We're going to have a fast track for innovation, get stuff out there. We pre-released our first product today for the whole of the Norwegian Armed Forces. So that's a huge success for us. So we're going to take all these innovations and get them out there, make them operative, and put them into use for the Norwegian Armed Forces. But we also, as you see there, there's a small arrow there, data back to research and development going on in the industry and research and academia. And that is our goal. We have started. We have a project now that we're doing together with the police, with the Norwegian Air Ambulance on search and rescue and the 330 squadron. We're collecting data from infrared cameras that are used to find people out in the Norwegian terrain. We think it's imperative to have a data sets that actually use thermal camera in the Norwegian environment, because we have different conditions than other countries that develop these systems already. So, and this data, we downgraded it, we collect it, downgrade it, and then we share it on our own service on Azure. And we want to invite collaborators in and work with us on this data. So, and we are looking for other projects where we can include research collaborators that don't have a security clearance, but can work with us on this data on our servers in the business cloud. So, military-grade data. It's hard to get, it's hard to use, and it's hard to share. We try to solve the hard to share. Thank you.
Thank you, Erik, for that, and for keeping on time and for keeping us safe at night. So our last speaker before the discussion is Christine Stansberg. She's a product lead for SAFE, which you've heard about earlier today. She's at the UiB IT division, and she's also the co-lead of NORTRE, which she's going to talk about today, the new national infrastructure for secure analysis of sensitive data.
Thank you. Oh, it works. Yeah, thanks for inviting me to talk about NORTRE, a brand new national infrastructure for sensitive data, both analysis and storage. And this is a joint initiative between SAFE here at the University of Bergen, TSD at the University of Oslo, and Hunt Cloud at NTNU in Trondheim. And it came as after a request from the Ministry of Research and Higher Education and the Ministry of Health, because they wanted to provide such a service to a greater audience than and across sectors and a broader range of users than we already do today. Am I clicking this on my own? Also works. Super. Yeah, so today I'll cover 3 different sections. I'll talk a little bit about the challenges associated with doing research and other analysis on sensitive data. Inge already covered parts of it. I'll not spend lots of time on that. I'll spend some time on the history of establishing NORTRE as a national infrastructure, but so the drivers, what were they? Why did we come into being? And then on the future, what are we trying to build and how will we enable more, better and safer use of sensitive data, which is sort of the vision that we have. Yeah, so the challenges, which has been covered a lot, but there are, the legal regulatory landscape is large and growing and conflicting. Some are enabling, some are regulating and constraining. We need to adhere to that, to protect a person's right to privacy and security. We have some organizational measures to try to help this. We make policies that we need to follow. We have procedures that both users and operators of sensitive data need to follow. We train users. We raise awareness among the population to what your data is being used on. All of this is important, but it's not enough. We need the technological measures as well to ensure that the data are safe and sound where they are analyzed. So to isolate them and to monitor what is happening and to ensure that everything is anonymized in there. And this is a technological fix for that, and a foundational fix on the technological side, what we call trusted research environments. They are known under many names, which you can see here. I don't need to read them, but they all share this common thing, that they are dedicated resources where you can store and analyze sensitive data, strictly isolated from the world and strict authentication to get in. And this is an example of a TRE, which we know well. It's SAFE, which we host here at UiB. It looks like a regular desktop when you are finally entering in, when you're authenticated. It's based on virtual machines. We also have some specialized physical ones inside there. We have Linux and Windows to your preference. So it's isolated from the world. That's one of the key principles. And it's based on strict control of who you are and what you are allowed to do when you enter. Also, import and export is controlled. We have several ways of getting things into SAFE. Everything is virus controls. We only have a secure way of getting things out, because you're not supposed to take sensitive data out of a trusted research environment. But if you do, it's all encrypted. Everything is logged, at least most of the things are logged all the time. And it's a very flexible setup where you can ask for more disk space, more GPU, or more CPU to your preference. And we have a range of pre-installed software. And you can ask to have other software installed if you need that, provided that this can work without access to internet. And we have altogether 3 such academic environments in Norway. We have SAFE, TSD in Oslo, and HuntCloud in Trondheim. And we have been around for more than 10 years, supporting most research domains, sectors, and hosting most of the health research that is outside the hospitals today. When joined together, we have more than 12,500 users, we have 2,500 projects, and we are host for registries, data collections, and archives. And I think we can jump on this. So why did the state decide now to build a national resource on top of these 3 academic infrastructures? So about the same time that our 3 different TREs emerged, there was a program running in Norway called the Health Data Program. And as part of this program, they were building a central data platform, which were supposed to host all the national registries, population studies. They would handle all of the applications for access and providing the data permits. They would link the different data from different sources, and they would also provide what is in this world is called secure processing environments, but it's almost like a secure analysis room or a trusted research environment. And they had a vision to make health data available in the right place in an enclosed and secure analysis room. This was paused in 2021 due to GDPR issues by the selected solution. And instead, we had an investigation whether our 3 infrastructures could serve part of the purpose, at least the part where you could have an analysis room where to put the data when you had finally gotten your application approved. And this was decided to move on with in 2022. So this was called the gjenbrukssporet, or the reuse solution. And this became the way forward for the Ministry of Health to provide secure analysis rooms for the Norwegian research society and also beyond. And then the health analysis platform was terminated after that. But in parallel, another thing was emerging called the European Health Data Space, which is both a legislation and an infrastructure from the European Commission, which will share health data across borders within Europe. So they're both setting the constraints on how to do this through the legislation and providing the infrastructure through which they will do this. And it's a very complicated and complex setup that they are building, and which Norway is also building now, with many capabilities that need to be in place for this to happen, including something called the Health Data Access Body, which covers part of the old health analysis platform, taking the applications and also granting access. And these need to have SPEs, official SPEs connected to them. So we joined the project together with the Institute of Public Health and the Directorate of Health in 2023 to start rigging this SPE capability for the state. And finally, in the state budget for 25, this elicited funding to continue these efforts on behalf of the Ministry of Health. So that's when we got the first joint funding as the NORTRE, the Norwegian Trusted Research Environments. Then we got a request from the Ministry of Research and the Ministry of Health if we could build a formal infrastructure based on the 3 infrastructures, because they needed to, they need an infrastructure that provides this service across sectors and domains, not just for research and not just for the university sector and the health sector, but also beyond that. Could we do that? And if we could do that, what would this structure look like? Because it needed to not compromise the academic freedom of the hosting universities. So this structure should be able to take steering signals from other ministries than the Ministry of Research, while still being hosted by the universities who do not take such steering signals. So there was a long dialogue with relevant stakeholders and back and forth with ministries, and in June they approved of our proposal, back and forth again, and eventually in January we were established and celebrated. We were invited to have cinnamon buns at the ministry to celebrate. So now we are on, and we're established as a consortium between the 3 university partners, with a board that has, in addition to our 3 universities representatives, we have 3 representatives appointed by the ministries involved, 2 from the health ministry and 1 from the research ministry. So this board is supposed to handle proposals for projects that need to be handled in such an infrastructure. This will go through the board, be handled in the leader group, and then operationalized as separate projects underneath. And just to show you who we are, so we are chaired by Gard Thomassen in Oslo, and our own Tore is representing us in the board. We have a leader group of the leaders of the respective infrastructures, and also a secretariat is being built at the University of Oslo, who is the hosting institution. So, to the future, what are we going to solve on behalf of Norway now? I've not talked so much about AI, but that is inbuilt as well, at least with the capacity that we do have. But how can we help out with the challenges of activating health data and other sensitive data for research and AI analysis? So we have 10 million NOK for this year. We're hoping to gradually increase this to 40 when we're running at full scale. And what I'm describing here as the actions we're doing, it's what we're doing in addition to the funding that we're already getting from the host institutions and the users that are already funding us. So it's not going to affect the ongoing projects and collaborations that we're having. What we're building here is coming in addition to what we already do. Yeah, so we're, in short, as a vision, trying to enable more, better and safer use of sensitive data, which is also what all of the relevant national and strategic papers are asking us and other actors to do. And we have split this in 3 main areas. We want to enable increased value creation based on sensitive data, or health data in general. That's what they asked us to do, but it's not going to limit other sensitive data as well. And we will help Norway prepare for the European health data space, and we will increase the robustness within our infrastructures. So more specifically, what we will do is to make it easier to move data from data holders into NORTRE. And those data holders can be data registries, where we have a particular project to try to have data more easily directly in from Health Data Service and into NORTRE, where we will distribute the data internally into the preferred room of the researcher. But at the same time, we're also trying to ease transport from the hospitals. That is not just a technical exercise, it's also a legal exercise on what does the hospital and the health net need in order to trust the research net where we are based. So this is another ongoing initiative that will increase the amount of health data which is available for research and AI analysis through that, in the cases that this is approved. We will spend a lot of effort to help Norway prepare for EHDS. We need to comply with lots of requirements for secure processing environments, a whole long list that we need to comply with, and we need to be certified according to ISO 27001, which will help us a long way along the list for EHDS. We will also support the health data access body and the data holders in sorting all of the data and how to share this data. And we need to build a new organization based on 3 separate infrastructures. That will take some time. We need to ensure that we have enough competence and redundancy so that we are not completely dependent on one key person. And we want to have an increased degree of self-service. And I see I've spent my time. I have one more slide that I can just skip if it's over. Yeah. To conclude, we want to make a foundation for advanced analysis on sensitive data, including AI, where the data can stay safely put and where we also have compute. Maybe not enough, but that can be discussed, how to get more. And so with that, we want to lower the threshold for using sensitive data without lowering the requirements for privacy, and to enable researchers and others to do cross-domain analysis to build on our existing and already trusted infrastructures, and of course help Norway along on the EHDS, which will be a huge challenge in the next year. So thank you. You can visit us on our brand new webpage and also join us as our new technical architect, which is out now. Thank you.
Thank you, Christina, and you can just find yourself a chair here, because the final part of this this seminar will be a discussion between 5 of the talks.
I'll get my notes.
Yeah, sure, get your notes. So I'll ask Håvard and Inge and Alex and Dumitru also to come up. And to chair this discussion will be Mihail from NORA, who's the CEO in NORA, our cooperative co-organizer of this event. So take it away, Michael.
Let's do it. On the chairs. The order doesn't matter that much. All right, welcome. Nice to be back in Bergen. This is now the 2nd year that we have this cutting-edge AI collaboration between NORA and UiB AI. So great to be back. And as Erik said, I also have been very lucky with the weather when I've been to Bergen. But when preparing for this panel, I had a few different directions in mind, but I thought there is so much competency in the research community, and sometimes the policymakers should come and listen to what we have to say. So I thought I should treat it as sort of a policy brief. Imagine that we're going to write a policy brief to some of the decision makers after this panel, and then I want to kind of pick your brains on some of those things. Norway holds some of the world's most complete state-held data: health records, genomic databases, welfare history, payment streams, and critical infrastructure. And it's almost all sensitive data. And if you look at the state budget of Norway, I think if you take health records, welfare data, social services, that makes up roughly 35% of the state budget. So economically, it's a huge potential for Norway if we could utilize this data in some way. But of course, it needs to be done in a safe and secure way where we also respect the privacy of the people and the state. So to make this policy brief, I thought there's 4 things. First, it's the opportunities. What are the actual opportunities with sensitive data? Of course, we talked somewhat about it, but also pick each individual brain. What is your goal? Second, the technical feasibilities. We have heard of some research infrastructures, but can we scale this to a national level? I think you gave quite a good reason that we can, now with the NORTRE. And the third is infrastructure and sovereignty. If we want to run, say, some of these foundation models on national infrastructure, can we do that in a sovereign way? Or are we now dependent on hyperscalers and their services? And fourth is governance. Are there anything when it comes to governance that we should think about and potentially change? So with that, my first question that goes to all of you, and whoever jumps first, I can allow you to start. So let's see who's more trigger happy. But the question is that we've been working on making sensitive data available for 15, 20, 25, 30 years. So there's been a lot of effort. And I think Tom touched on it. Should we just send the data to the computer, or the compute to the data? So there's been a lot of back and forth. The question is, now we have AI in addition to sensitive data. Is there something with sensitive data that we should reconsider now that we have these more larger foundation models that can add extra value than if we think about sensitive data alone? I'll start with you, Inge.
So you're thinking about the large language models, whether they kind of change the picture.
Yeah.
I would think to some extent, if you're thinking about electronic health records, for example, there's a lot of text written by doctors about patients coming through that is not, captures information that is not so readily available. But with the use of large language models, there's a potential, of course, to extract more information from those. So that would be a kind of a somewhat change compared to before the large language models. Of course, we have all the previous data on registries and so on. I'm not really so much affected, in my mind at least, by the large language models. So one could do some validation maybe to see what, if the information extracted from the free text, so to say, is consistent with what you find in the more tabular data. Yeah.
But I'm thinking not only with large language models, but now you can build multimodal foundation models potentially with the data. You can have, genetic data, you can have health records, you can have financial data, and you can build quite complex models with those, which would require very different type of compute, very different accesses, linking data sets, and so on. So that's kind of more my question. Is there some opportunities now with sensitive data when we apply AI on top that wasn't there before? That we does that change the way we think about how we should structure the sensitive data?
So let's think in a utopian world where you could have access to all this data, not each one personally, but one entity, let's say, and feed that to a large language model. So imagine what kind of inference you could draw that you can't do now. So technically speaking, is that possible to do, even if there will be one entity to feed that into a computer? So I don't think any European, there are these AI gigafactories that are emerging, so maybe you could do that there. Yeah, so in terms of opportunities that you would potentially have this infrastructure, the models feed all this sensitive data, and you could find so many interesting problems and extract patterns that could change policy, the way how it's formed. So definitely opportunity is there, but of course the question is compute and data access, which are the difficult parts as far as I can see them.
Any other thoughts before we move on?
And permits, who would you give access to all of this potentially very harmful data?
Would there be, so that's kind of the question. Are there other things to think about? So then who should actually have access? If that was possible to make this one space or link different spaces, how would you steer access? Should it be researchers? Should it be certain parts of the government where you can actually that make the services. Maybe it was NAV that should have that access. Maybe hospitals.
You could think of trying to use this if you kind of free yourself a bit from these regulations to optimize use of NAV resources by looking at financial transactions and resources that may not be public in the same way as NAV is normally using. But that would be kind of stepping beyond what we would do in a society like Norway. But you could, of course, also maybe think of imaging data, more traffic data, that is not so sensitive, but that may be put together and help enrich, help see new patterns that would still help NAV and policy making.
Alex?
Yep. So your question was if we should change anything with these new advancements in AI, and I think that we have two distinct issues here. There's the issue of the data itself and the compliance with law, and then there's the issue of technology. And as technology evolves, it doesn't necessarily mean that the way of handling this data should. I think that the way of handling the data should be very robust, regardless, with stuff like access control and all of these, and properly separating the models and labeling them and so on. And that, I think, is the main blocker as of today, because we already have so much data that we could analyze, but we don't have the consent and the legal basis for analyzing these. And so in that regard, adding any form of AI on top does not change that.
But so how, if we wanted to utilize this sensitive data, like how would we solve that issue then?
We would solve it in the same way that we do today, with those purpose-based analytic projects, where you have a very strict reason why you're using it, and then if you apply more technology and better technology on top, good, so be it, but the underlying infrastructure remains the same.
So thinking back to some of the presentations today, we had the UK Biobank as kind of the gold standard. You talked about the way you have your platform internally in VIPS, which is basically also building a UK Biobank, similar but inside of VIPS. In Norway, we have all these databases, all this data, but it's fragmented around. So how do you reverse engineer your way back to having a UK Biobank for Norway, or for like you've done in VIPS? Is there any way of, because you start knowing that you need to build this platform, but our problem is that we already have the data. Can we now build that platform, or do we have to start all over?
Is that for me?
Yeah, yep. For you.
So in some regards, we did kind of reverse engineer, because we merged VIPS with MobilePay a few years ago, and we had to rebuild the data platform from scratch. And some of the concepts of data modeling still apply, right? So the basic concept is you have scattered data sources, and you want to bring them in one place. And it's never too late to start on that. And I would say that the impact of doing that in a central platform is significant and worth the effort, because it's far better to have a centralized place for governing all of these than having them scattered across multiple organizations.
So your question, I think it's the answer is that, so data is there, right? The question is, how can you
how can you get the value out of it
and connect it, because that's where the value comes, when you connect things, right? So the main issue here is not technological. We know how to extract data, link data, put it together, train models, and so on. The problem is governance. So like, will those that sit on this data be willing to change legislation, procedures, organizational things? So I think that's where the main problem lies.
I'm not sure if they would want to build one more national platform again after the previous crash, but some functions are already linked. You have for the health data at least, you have the health data service, which is one place where you send your application that then gathers the data from the different registry and data sources, which are connected. Of course, there are many sources that are not connected, and then give you linked, pseudonymized data back into your trusted research environment already. So some functions are linked. And you can also have statistics data linked also with that. And with the EHDS, there will be even a much larger scale when you're handing out all of the health data that Norway is hosting, which is a lot and very, very complicated, and everything is health data. And this poor health data access bodies, however they will look, we will know more in June when this will be proposed, the structure of those. They will have this function of actually linking and delivering out anything based on health. That is another big, if not platform, then at least function that will do this.
I think building a new monolithic system that captures everything is probably not. But to have something project-driven that will actually have a kind of use case and extract data, maybe through the health data service platform, but also integrating other is a better way to go, yeah. And to have some pilots, maybe in public-private partnerships, that could be something to look at. Yeah.
I have a question. So what happens when you have 3 new projects that arise that need to have similar data processing?
Then you hopefully have some synergies. Yeah. But for example, a hospital has hundreds of IT systems and legacy systems from 70s and 80s, and how to integrate and run these together is already a big headache. Yeah. So how to run one system that gathers all the data. It's not 2 systems to be merged. It's quite a big, complex
I think I want to move on to the next topic here, but I hear that there are potentials, there's legislation, and how should you actually structure it via a platform, not building a new platform at least, but connecting what we have in a better way. Technical solutions, you talked quite a lot about it, Elisabeth, but if we're not having one platform where you access, but you have to have access to different type of data from different platforms. Maybe you, Håvard, you talked a bit about encryption, federated learning, different type of methods. Can this actually scale up to a national level? And can you say a bit about that landscape of treating sensitive data, sending back and forth between different platforms?
Yeah, so I mean, I have to answer from the perspective of encryption, because that's what I do, but it doesn't scale well, right? So as I showed, this federated learning with encryption on top, yeah, that is actually useful, but if you have to compute on encrypted data in a large scale, we have a problem still. So the good thing about the encryption is that it doesn't compromise on the security. You really know what you are getting there, yeah, the scalability of the computing issues is a problem there. So, but I see encryption as an enabling technology that is able to say not bypass the legislation, because the laws are there for a good reason, right? But to accommodate them in a sense. So, yeah.
But are there other type of techniques that we should think of that could be developed to handle these type of problems?
Yes, I know only about the cryptography domain, so to speak. So there is another technique. Today I only spoke about what's called fully homomorphic encryption, but there is something called multi-party computation that does sort of a similar thing. But there's also cryptographic techniques, and it has its own computational drawbacks. Lots of communication bandwidth that's needed there. So unfortunately, it doesn't scale that well up to a national level and so on. But on individual projects and for specific problems, indeed, I would suggest the encryption methods. Yes.
But maybe Tita and Elisabeth as well. You work with open data spaces. What are the limitations to what we have now? Like, what's holding us back? Or European health data space, for example, would it solve everything? Or what is the problem with it, if there's any problem with it?
It's not built yet.
No, I know. I've heard about it for I don't know how long, 10 years.
But that is maybe the biggest problem now. It's not built. Everyone is just stressing a lot. All of the countries in the EU are stressing so much to get all of the capabilities up and running.
But do you think when it's built that it will actually work? Or would it be like the health analysis platform in Norway, where we put in billions and then it amounts to nothing?
Yeah, hard to say. It needs to work.
I think we need to build on things we already have that are functional, including the trusted research environments, what we have been doing within the Elixir system, and also in other research infrastructures that have some of the pieces at least required for making the EHDS fly. So from Elixir side, we are working across countries because we have the technology for the genomics part of this and towards some of the clinical information, and that of course needs to work together with the trusted research environment. So the Untrust project that you didn't have time for is a European one coordinating this trusted research environments and kind of bridging between these and some other structures and the European AI factories and so on. Hopefully we are making steps in the right direction.
Because at least, yeah, Titi.
Yeah, so you asked about data spaces. I mean, data spaces get you from, what data is there to can I access the data legally, right? So these ecosystems, help you with metadata for the data sets, legal information, contracting, and so on, right? But they still don't solve the problem of actually doing something with the data. That has to sit in some sort of secure environment, whether it's, maybe in a data space, maybe outside. So they help solve some problems, but, it doesn't cover the full life cycle of what you want to do. So I think data spaces are good, help for some things, find data that's out there, all the mechanisms to somehow get access to that data, but what you do with the data, it's unclear.
Yeah, my next question, or what I was thinking when you guys were talking with the health data spaces, the European health data space and the health analytic platform that failed, because we had environments in Norway that already had done it in some way at the universities. So you think, let's reimagine, go back to when they planned to build a health analytic platform. If that was given to you now who have NORTRE, do you think it would have been successful if you have been given the task to build it?
So the scale was very, very big for the whole health analysis platform. It was not just providing the secure processing environments, it was all of these other functions as well, which are vast. So if we should do that successfully, we would have needed to gather a lot of competence to be able to do that. And hopefully we would then build on already existing initiatives that would hold that competence instead of trying to build it from scratch. I hope we would have done that. I don't think it will be an issue.
So just before moving on, then the encryption method, if I hear it won't really scale here. You might solve specific problems with it, but scaling it to a national level might be difficult.
It has to be looked into at least, right? It doesn't come automatic or for free.
And then you have the data spaces. That's where we can still improve and make them larger because we have some of the competency and build on what you have stone by stone instead of going out with this big health analysis platform. So yeah, I'm just thinking about the conclusion here. Okay, moving on to sovereignty and compute. Would you say that compute and sovereignty might be one of the missing pieces here? If you just throw compute on the problem, is that a good solution? Inge?
Well, I think for compute in context of AI, we, at least at present, we are depending on collaboration with the neighboring countries and with, for example, with Lumi and AI factories to scale things up. But of course, there's nothing stopping us from doing things on our own, except for political will and funding. But it might be better to work with in the European and Nordic context. But to build our own foundational models and to use those in a good way, we need more compute.
But how does that work, Lumi, these AI factories, are they set up to handle sensitive data?
I believe that's part of the setup, yes.
Yeah.
Yeah.
They want to test it, and we will take part in that, and we are testing internally a mini version of that by trying to send data from SAFE to compute within the Sigma 2 cluster that resides within TSD. So that will be sort of a pilot that they can repurpose when they want to send data from Norway to Lumi, if that is possible. But then that would be provided that the compute cluster at Lumi was also secure. So the whole route from sending data from one of our TREs to Lumi would have to be secure and also ISO certified and compliant with EHDS, because we would not want to compromise that. And also the data holders providing the data would never give those data out if this was not in place.
Thinking, because we're talking a lot about the national level research, Alex, from a VIPS standpoint, from someone who actually needs to operate in the real world, things needs to happen fast. Encryption method we talked about. Is there anything of what you heard today from a research side where you think, oh, that's really cool, I can take that back and implement it into VIPS and make our platform better?
I don't know about implementing it into VIPS necessarily, but I really liked the encryption that Håvard mentioned. And I thought that it's a very cool and way that I hadn't thought about before of solving the organizational problem of sharing across organizations, right? Like with the different hospitals, maybe share data across different banking and financial institutions related to fraud, right? Because fraud data is such a rare data to deal with, and perhaps encrypt that data, have it in a central database, and then have ML models trained on top of that. I think that's maybe something that I could take away from this.
Just because you mentioned sovereignty, right, in this one. So one thing I've been thinking about and that I want to emphasize is that cryptography increases sovereignty in the sense that it really takes away the need to trust other third parties because you control the data yourself. And that applies to like any kind of cryptography, not just the computationally heavy one that I talked about today. So I would just encourage everyone to actually look into the use of crypto whenever you want to keep control, in the sense that when you send data now to someone and you have signed an NDA, so you trust them to not do anything bad and so on, and maybe they won't, but they might be hacked, right? But if everything was encrypted and only you have the decryption key, then it's like, okay, it's no problem. So.
Yeah, so sovereignty could be a very important part of, or encryption could be a very important part of sovereignty.
Yeah, it actually enhances sovereignty.
But then you have the scaling problem. If you need, so for VIPS, for example, with Olga, you need things to happen, you know, in, was it 500 milliseconds or whatever?
Yeah.
So that's, yeah. But I think for training purposes, if you had to train a model, you can do it in an encrypted way and then deploy the actual model that you done with. Yeah. So. If now I would just move on to the next question here. We have so much data in Norway. If we could link kind of data across welfare, education, income, and so on, and build now in a utopian world, Titi, a foundation model with all these databases in Norway. So Inge, if we build a foundation model with all this sensitive population data, do you think it would actually be valuable? Like how much, if you think about a third of the state budget is healthcare costs, whatever, how much could we save if we build a foundation model? Or is it just imaginary thinking? It's so...
Yeah, of course, we could throw out a number and say, like has been done from the ministry, saying that 80% of government should use AI or something. But no, it's hard to speculate on that. But as you say, it's a big portion of the state budget, and I would think that it would be good to have some kind of use cases in mind when building this foundation model. So it's a good place to start. So of course, in terms of you could Imagine cutting costs in the administration. So NAV is a big employer. There's a lot of processes that are heavy. We saw a debate yesterday on NRK about the long processing time for getting sykepenger back from NAV. Many things can be automated by simple uses of AI without having the... So there are things to cut there as well. And then on top of that, you could probably use the resources more tailored where they are really needed towards the individual citizens as well, if you have a better overview of a situation, get better insight into the patterns.
So, if I can say, I think definitely you can get better information on, how you could, where the problems could be, where you could save. Now, whether that, actually materializes in policy, taking that evidence that we could produce and cut the cost, that's a different story. So I think you can, with building these large models on this sensitive data, you can bring better evidence that, cut from there, or you cut, this cut causes another potential cut, so you bring evidence, right? Now, if the politicians will take that evidence and change policy, it's a different story. So I think you can come up with very good stories, use cases, backed by, numbers. Now, whether those will be used in the right way, we don't know. We can't quantify that.
The right people, eh? But just one thing is just the saving money and cutting costs. But what about better outcomes for patients, for the people? It's not necessarily about saving costs, but also a better outcome for the citizens of the country.
Sure, kind of personalized medicine can potentially, has been shown to do that, to cut costs, of course, but also when you do get some medicines, it has side effects which are painful and costly also for the individual. So and if you can detect or target screening programs to detect early onset of disease, you can save costs and have better welfare for the citizen. So there is potential. And we all wear, or at least many of us have wearables that can help do this, and that should be integrated in the data that we generate ourselves, should be integrated somehow into the healthcare system, I think.
Because now maybe you're not an AI researcher, but there's a lot of hype in AI. Foundation model, throw all the databases together, build this one fantastic model that will solve all the problems. Is there too much hype around this, or what's your feeling around that? Now I'm creating hype with this conversation, like can we beat a model, can we do this, can we do that? Are we grounded in the real world in this?
That's a big question.
That's a big question.
That's what the big stock markets are all about these days, with a lot of the biggest companies on the stock market being AI companies or AI-heavy companies. So
you're laughing at
I'm not even in the AI field, so I just have my own personal thoughts on this.
Those are fine.
No.
No? Truly academic, unless I know it 100%, I won't share. Titi, you raise your hand.
Yeah, I mean, what I noticed recently is that, okay, you have these large language models, they are great. Community acknowledged their limitations, like their statistical hallucinations and so on. So now what I see, it's a lot of things that, this agentic AI, so you build all sorts of things around these LLM models that, try to use them for solving certain type of problems, automation, and so on. So I think there is a move now from, okay, we have seen large language models, LLMs, they are great, they have limitations. Now let's build some, agents around them. So I think it's, the LLMs themselves, okay, they are important, but the emphasis, I think, moves around all these things around them?
I think there's definitely an aspect of hype, but there's also so much value to get out of this. Dumitru mentioned LLMs, and these LLMs can be more effective with the more context we give to them. So utilizing these tools, for example, in my work life, has accelerated my process of development quite significantly. And there's more and more processes that get automated, some just through normal code, but some also through AI. And there's other types of AIs that I also think have a lot of value, like creating networks between individuals, like graph networks that require more compute, and then inferring maybe the strength of a relationship between people, finding trends that exist in the data. And there's enormous potential there. But then again, I always go back to the question of whether we have consent and a legal basis for doing a lot of these things.
Question, what would you use it for if you knew the links between everyone?
Yeah, you can tell how different behaviors propagate through the system. For example, let's say you're a trendsetter in our system and I'm a follower, and when your spending increases, mine follows suit. Mm-hmm. And maybe when you adopt one product, my product follows suit, and so on. Okay. This is not something that we do today, but it's something that could be possible.
Of course, I also like to remember the example of AlphaFold really solving a big question, a big challenge in science. And I think we'll have more of those breakthroughs where AI is coupled with really deep domain knowledge and have more tailored AI that provide value both for science and for welfare.
Mm. So if move on to the last part on legislation and governance. Is there something, Inge, you spoke about it, maybe that the governance is a bit too strict sometimes in terms of access? I think Tom also mentioned that they spent now 2.5 years to get access to a data set, to do two different data sets they want to link. If we were to change something about the governance or legislation, what would it be in your head?
I think we are too much on the privacy concern side. Of course, there needs to be a balance, but we also have an obligation to use the value in this data for the common good. And the setup that we have is probably a good one, but in practice, it takes too long. Yeah. So there can be technical aspects to this, and also implementation in the governance model that is to be improved.
Christina. That is underway with the digital omnibus that the Commission is now trying to set out to ease the way for AI analysis so that EU can speed up value creation based on data, according to the Draghi report.
But are there any other things that you would want to change?
Yeah, I'm on the protective side, so I will listen, and then we will make the adjustments when the laws change.
I think first Alex and then
yes.
Dumitru.
I'm also on the protective side. I think user protection is the most important. But in terms of sovereignty and the tools that we use, like the cloud providers and so on, they're all American. And I think they're American because, of course, that's where the budget is, but also that's where there's ease on restriction compared to the EU. And so I think we need to make an effort to allow different European companies to be competitive on the global stage by easing off on some restrictions and making it less bureaucratical so that they can thrive at the same level. And so companies like ours can start using more and more European products.
But are there certain things that if legislation was changed, VIPs could do better? Or are you very happy with the restrictions that you have in terms of the service that you want to provide? Or could you deliver better services if you change some of the legislation?
Yeah, there's definitely blockers in terms of legislation. Whether it's good or not is not for me to decide, really. From the perspective of data analysis, there's so much that I would like to do without regulation. But of course, it's there for a reason, so we respect that.
maybe more a joke side, but I would try first of all to speed up the case processing time in Norway. Like if we have seen this example of asking access to a data that takes, how much was 6 months just to process. I mean, and I also had a recent NAV case that they promised to solve in 6 months, and I had to call them in the 7th month and argue with them that, you know, you should provide within 6 months the answer. That's what the law says, and you know, if.
So yes, I mean, I'm also on the privacy side, I would say. Cryptographers usually are. But I would like to see more efficient legislation, as you can say, referring to your case. I would also like these technical solutions that I come with and others come with to maybe be, if not baked into the law directly, at least there be a forskrift or some understanding of how the law should be interpreted that includes that. Because I've seen, as a cryptographer, I've seen that we come with these solutions. Look, this solves your problem. And then you speak to some legal research and say, well, because even if it's encrypted, still sensitive data because the decryption key exists somewhere. So it's like when you have ciphertext, can you then bypass and then all laws and say that it's, no, this is not sensitive data, and then someone else will say, yes, it is. So there is this hesitancy of does the law apply now or does it not apply? And this would be great to have clarified, such that when we come with these solutions, then it's clear that, okay, we can disregard these regulations, they are taken care of, and only these others apply.
Just to support this, it's the same for synthetic data. You know, we have technical means to prove some guarantees, which is the same case as in encryption, but you know, people are suspicious whether it's encrypted data or synthetic data. Okay, are we still allowed to use it in the? So I think some sort of certification bodies that, you know, either your encryption mechanism or certain synthetic data generator could be, you know, sealed, certified that okay, this can be used. I think that this kind of services could help in speeding things up.
Yes, agreed.
I think we need to bring it to a close, but very helpful input. If I were to go and write my policy brief, maybe a bit less positive than when I started, but there's still opportunities there, I think. If we could access data, link databases in some way, we have the expertise in NORTRE, how you build that. We have methods, encryption methods and other methods that we could use, and we need to figure out where do we need them, where can they scale, where can they not scale. In terms of infrastructure, we want more compute. We always want more compute, but we have now trials going on with Lumi, with supercomputers and the AI factories that could potentially solve some of that constraint on compute. And then if we sum up legislation, we should keep it on the privacy side, but it's faster regulation. Like, we can have the same regulation, but it needs to be the process time until they come to the conclusion they want to come to should be shorter. That's my quick summary on that. Should we take a round of questions or should we cut it? We're 1 minute and 40 seconds over time.
We can do a couple of questions if people have, I think. We have another 30 minutes for a bit of fruit and mingling, so we take 5 to 10 minutes of those. If there is any questions or comments.
I think it's probably then late enough, so yeah. Thank you all. Great.
Thank you.
Thank you.
Okay, so thanks everyone for coming. Thanks for, of course, to all the speakers, and not least to all the tens of thousands watching us online. I'm joking about that, but the first UiB AI seminar was on large language models. It was I think it was in February 2023, and there were actually more than 40,000 people who watched it, so, so there's a possibility. Our next UiB AI seminar will be next month. It's a cooperation with the Universitetsfondet. It's on AI alignment. This is about how can we, if possible at all, make AI systems work the way we want them to, because they don't always do they? This will also be a full-day conference with speakers from all Europe, including the AI expert in BBC, so it's very interesting. You can find information about this and other UiB AI seminars on the UiB AI website. Then I also want to inform about NORA seminars, because the next upcoming cutting edge is on 8th of May on sovereign AI infrastructure. You can follow that online, or you can go to Oslo and be there live. And not least the yearly conference, which will be on 1st and 2nd of June in Oslo. This is a yearly event for 2 days with lots of interesting stuff on research, but also on applied AI stuff organized by NORA. So I encourage you to come there and just check out the NORA website for other seminars happening. Lots of stuff going on there. So thanks again for the cooperation, Mihail. And there is some fruit, as I said, and some leftovers from lunch, some juice, some coffee maybe. So hang around and talk to the speakers or to each other for another 30 minutes or so. And hope to see you back in a month. Not here actually, but in Nygårdsgaten 5, the next one. So thanks for coming.